So just a second. It's now starting the YouTube stream. It lasts. Yeah, okay. And now I try to. Oh, sorry. It's not visible. Can you see something?
No, we only see the VOC bars.
Oh.
Sort of compressed in a quarter of the screen.
Yeah. Mm.
You can ask Anne on the spot. Děkuji moc. Ale neběží to pořád.
The following message is best viewed on an oscilloscope.
Okay, děkuji moc. Okay, so sorry for technical problems, and now we can start.
Okay, so I'll start again. So I'm Julie Malclès, the chair of this session, and I want to welcome you to the first Higgs session, which will be dedicated to future colliders and updates on rare and exotic decays. So just a few reminders, the talk are 15 minutes long, and I will give you a notice at 12 minutes, 3 minutes before the end of the talk, to let you know that you have only 3 minutes left. Then the Zoom will stay open for discussion after the session if one wants to ask further questions. Also, if you have questions, you should raise your hand and maybe introduce yourself before to ask it. And also speakers are encouraged to share their videos. And I think that's all. So the first speaker will be Matthias. And yes, speakers are asked to share their slides. So Matthias, please go ahead.
Matthias, you are muted.
Good afternoon, everybody from Virtual Prague. I'm going to tell you about the Higgs trolling and double Higgs production at the high energy runs at GLIC. So CLIC stands for the Compact Linear Collider. It's a proposed E+ E- linear collider, which will be built in several stages. The final stage at 3 TeV will have a length of 50 kilometers. It's supposed to sit around the CERN vicinity, and that can be achieved by having high acceleration gradients. And it was demonstrated that these, which are projected of 100 megavolt per meter, can be indeed achieved using the two-beam acceleration scheme. As a linear collider, it's also possible to have polarization on the electron beam, and it will be built in a stage construction up to 3 TeV starting in 380 GeV. What you can do there is you can perform several high precision physics measurements, mainly in the Higgs on the top sector, but due to the high energies which can be reached, also BSM studies can be performed. Also, these can be inferred indirectly also through the high precision which can be achieved. We have lately done a new optimized detector concept like that. It's an onion-shaped like detector where the calorimeter, which are very fine-grained, sit inside a 4 Tesla magnetic field, and it's an all-silicon tracker. We have several simulation studies of physics performed and also performance on the reconstruction. All these studies have gone into an input to the European strategy update where you can find all details, both about the accelerator and the detector in that link. And the first beams, should it be built, could be realizable by around 2035. Now, the Higgs production at CLIC is going over the measurements at all these 3 different stages. Here you see the cross-section plot, and here the 3 stages where the measurement will be performed. It has access to several production channels. For example, the CH Higgs-Strahlung will be the dominating one at the first stage. At the 3 TeV stage, it will though be significantly less. And I still will show you why it's actually important to still study it, no matter if the cross-section goes down by that much. Then at the higher stages, you also will have access to the double Higgs production, and there you can extract the Higgs self-coupling. For example, here you see 2 diagrams where you see the contributing diagrams where we have the sensitivity to the Higgs self-coupling coming from. Now, the comprehensive overview can be found in this paper, and there are several precision measurements of the Higgs couplings, of the Higgs mass, and also the Higgs width, which can be performed. But now let's go into the 2 main topics of this talk. First of all, it's the Higgs-Strahlung at 3 TeV. What I have shown you before, the cross-section, at the first stage of 380 GeV, it is actually by far the dominating production. Now, it's important at this stage to determine the HHC coupling, which is done via the recoil method. Now, why is it still important to look at it at the 3 TeV stage? At the 3 TeV stage, the cross-section for the HC production is significantly lower, but what we have there is that we have an increased sensitivity to BSM effects if we use effective field theory to get a grasp on that. So if we look here on the scales which can be reached in terms of the dimension 6 operator coefficients, we see that the 3 TeV gives us an edge. And if we even factor in what of this additional edge or contribution comes solely from HC, that's the difference between these light bars and the dark bars, where the dark bars then include the HC constraints. So basically that one is the reach which we get in addition, which is for some of them a reach which is a factor of 2 just coming through HC. So it's very important to also study that. We know that one is only using the rates. Now, in addition, angular distributions, where you look at several distributions, for example, the Higgs decay direction with respect to the incoming positron beam, or the event decay plane of the C and the Higgs, there you can get an extra edge and even increase your sensitivity any further. That study was performed by theorists looking at C decaying into 2 leptons. Nevertheless, we know the all-hadronic channel delivers most of the statistics. Nevertheless, it's more challenging on the backgrounds. Now, what we thought, what we could achieve, the precision with significant statistics enough to actually produce these asymmetry distributions by concentrating maybe on the higher energy. And if we go for high energy topology, it means we have boosted jets and we have jet substructure, which we study for the first time in this new detector model, click that. Also for the first time, we look here at the B tagging within boosted jets in the plus and minus collisions. Now, what does a boosted topology mean? We look at effective center of mass energies over 2.5 TeV. There, the events are characterized by having two back-to-back high energy jets. One jet is the C, one jet is the H. Each of those jets contains two subjets. Now, if you look and consider that H decays predominantly into B quarks, which is what we look at for our signal definition, B hadrons have neutrinos in their decays, so energy is lost. But since we go for a very boosted regime, we can in fact use the MET in our event, project it on the jet, and recover most of this energy. So if you look here, the original reconstructed jet, and we correct that, we see if we compare the reconstructed jet energy with the H boson matrix element energy, and then we see that we largely recover all these low events which come from the neutrinos escaping detection. It also helps us to decrease the width of the reconstructed jet, and also there, the tail to lower masses coming from these neutrinos is also largely recovered. Once we have done that, we can also order the jet by the mass, where the Higgs jet is the more massive one. And if we look how good the assignment is for the reconstructed jet to the boson, then we indeed get it right by something like 98%. Now we then also use a BDT where we use jet information and where we use substructure information. And what we get in the end is that for our HC, all hadronic events where H goes into BB bar, which is our signal definition, we have an efficiency of around 50%. And if we include then all other Higgs decays into the selection as well, we have something where 57% of all events remaining after the selection come from single Higgs. In the positive polarization case, there, some of the backgrounds are largely reduced, particularly the 4-quark background, whereas almost nothing is reduced for the signal cross-section itself. So there we achieve even a purity of all the events of something like 70%. Once again, the efficiency of the signal definition where H goes into BB bar is around 50 to 6%. So we achieve a statistical significance on 4.4 if we use the beam time for negative beam polarization. The positive beam polarization runs, that's 1 inverse autobahn in terms of integrated luminosity. There we achieve 8.8% for a combined result of 4.0%. We also had already a guess we made on the systematic uncertainties coming from the B tagging shape, the jet energy scale, the luminosity, and the beam polarization profile itself, and other beam background related uncertainties. And these are found to be smaller than the statistical uncertainty. Now, is the statistic sufficient to extract actually an angular shape? You see here that we have enough events that we actually can have sufficient statistics to actually get down something there. What theta is now the angle between the positively charged quark and the original Z direction. What we determine here is the subjet, which is assigned to the positively charged quark, and that gets it right using jet charge to something like 60 to 40%. Now, let's go into the double Higgs production at click. Double Higgs production only delivers really, really few events at the first stage. So it's only possible to see it at the higher energy stages, where we see that the CHH production cross-section goes down from the second stage to the third stage, whereas the second production process, which is HH nu, that one increases significantly once we go to the highest energy stage. So it goes from a couple of hundreds events to a couple of thousand events. Now, that means HH nu is sufficient enough to have at least a differential measurement even there. Now the impact of beam polarization compared to unpolarized beams, the HHC rate is only minorly increased or decreased. Nevertheless, the cross-section is modified by a factor of 1.8 for the HH rate. So to have beam polarization does give us an edge in this. Now, we have now two processes. HH is studied in full simulation at 1.4 and 3 TeV. So at the second stage and the third stage, using for the generation wizard and Pythia 6 for the event generation and an older detector model. It's measured in 2 channels if we consider the double Higgs and the 4B quark channel and the 2B quark channel. Now for CHH at 1.5, we only have an estimation. The estimation assumes a 20% signal efficiency and a signal to background ratio of 1 to 2. We have nevertheless a full simulation study, which will be soon going public in a node by next week, which we have done at 3 TeV using the new Glick detector model concentrating on the 4B channel. What we found there is that our evidence, which we have for the previous guesstimate of 3.3, goes down to 2.4 sigma, maybe more to be gained if we would combine these results. Nevertheless, it also shows that the efficiency, which we assume it is 20%, is something which we can achieve. It's something between 17 and 21% to reach 2.2 to 2.4 sigma. So there is quite a plateau, which we have for quite some efficiencies. If you want to have more purity or if you want to have, more on the efficiency. Then for the HH nu, we get an evidence of this process at 1.4 TeV2. 3.5 sigma is the result which we have there. Nevertheless, with 3 TeV collisions, a 5 sigma observation is already possible with an integrated luminosity of 700 inverse femtobarn, and in the end we will have a 5 attobarn inverse in total luminosity. It's 7.3% on the cross-section. What is important here is that the backgrounds are rejected using B-tagging information. So that's, for example, the B-tag sum of the first 3 leading B-tags, and you see that the HHC signal is very peaked to having 3 well-identified B-jets, whereas all the backgrounds for diquarks and for 4 quarks is far lower, and even the 6 quarks, where you see here the peak at 2 coming from the TD bar contribution there, where we have also 2 B quarks, that can be largely reduced just by placing a high cut on the sum of the B tags. Now,
3 minutes left.
Yep. In terms of the Higgs self-coupling, what can we do? We can use the total range rate of the measured HH events. There we can then extract the self-coupling, and the cross-section is then also dependent on the ratio of the actual triple linear self-coupling and the one which we have of the standard model. Now, CCH is monotonously increasing as modification, and HH nu, we have a certain, let's say, valley. The problem is that just using the rate alone creates an ambiguity which we cannot get rid of only if we look at differential distributions. If we have differential distributions, the variable which was studied and found to be the most sensitive is the invariant di-Higgs mass. And that one then can distinguish between values where the modification factor is smaller than 1 and larger than 1, which then resolves the ambiguity which we would have in the cross-section only measurement. So it's important to also do a shape study. Now, the measurement in di-Higgs events, that one we get mainly from the HH nu into 4B's analysis. So here it's also selecting the B quark content, so B tagged 4 jets, missing transverse energy because of the escaping electron neutrinos, and then we use boosted decision trees once again as input from the jet observables. Then the signal yield is something like 766 events or a background of 4,500 events. Then you do a template fit for different GHHH values, and there you use the di-Higgs invariant mass in 3 bins of the BDT score as observable. What you can achieve then is -8% on the negative limit and +11% precision on the higher end. Now, you might think, what happens now if we do the single parameter fit, which I have shown you before, and use instead of that a global fit? Now, the global fit could potentially reduce our sensitivity by quite a bit, but these studies were performed too, and they have shown that going to a global fit and using only the individual one parameter fit, that this gives very similar results. Now, why is that? The double Higgs production we know is not only affected by modifying the Higgs self-coupling, but the Higgs precision Higgs program, which we have at all stages, constrain many of the other parameters, which are of interest for the di-Higgs production to a large extent. And then you also see what going to the highest energy stage gives you, in addition to only measuring it at 1.5, so the second stage. Now, this global fit was also done on the previous, more not that tuned cuts yet. And the tuned cuts give us also an edge. So that result might also be slightly better, but we also think that the global and individual constraints will still be of a very similar account. So to summarize, we can measure the Higgs Strahlung in an all-hadronic signature with a precision of 4% at the 3 TeV click energy stage. Also, we have sufficient statistics to look at differential distributions of the angular variables in the boosted topology alone to provide valuable input on the EFT fits as well. Then the double Higgs production at click is measured in CHH and the HH-nu channels, both at 1.5 TeV and 3 TeV. There is a unique opportunity of click to measure that Higgs self-coupling because it's the collider, the lepton collider, which would provide us with the highest center of mass stage. So it's a direct measurement which you can do in E plus E minus. And we see if we go for 1.4 TeV, where we have, you know, a 30% or 60% uncertainty on both sides using this rate analysis only. If we use differential information, which we get by going to really, really high 3 TeV leptonic energies, then we can get that good result of -8% and 11%. Now, the global EFT fits lead to similar constraints than doing a one parameter only fit. And with the achieved precision numbers, we have also sensitivity to interpret it in several BSM models. For example, we can say something about baryogenesis. Thank you.
Thank you, Matthias. So questions. I see Katharine raising her hand. Please go ahead.
Yes, hello, this is Catherine Meany
Yep.
from Atlas. I was wondering, so at the LHC and the HL LHC, we see that like BB gamma gamma and BB tau tau provide much better constraints on the self-coupling than, for example, 4B. And I know there's not the issues with hadronic backgrounds. I was wondering if you'd looked at these channels at all yet? No.
I mean, the channels which we looked at were indeed only these which I have shown you. I mean, in the analysis for the CHH, they are always included, but they are not targeted. So you get obviously still a contribution from the channels which you didn't target your selection on, but it wasn't studied in detail or just focusing on other variable channels. So I cannot give you any further hint on that. What I can tell you though is that obviously our backgrounds from hadron backgrounds are just a lot lower than at the LHC. So that is why we typically go on full hadronic ones, and they are usually precise enough.
Okay.
I mean, that's why we started out with that.
Yes, that's totally understandable. I'm wondering if, for example, BB gamma gamma would give you a better mass resolution, so you would be able to better, you have more shape information in HH distribution on side. But it sounds like you have.
Yeah, I unfortunately cannot tell you yet.
Okay, well, I await that eagerly for when it appears. Thank you very much.
On the same line, I was wondering if for HC you could study also if you use Z2LL and you have the constraint.
Yes.
Would that be interesting to do, or is it useless compared to the statistics of BBBB?
So what we wanted to find out if the statistics edge gives us something compared to the precision edge. Nevertheless, we saw it indeed does. Because for us, the problem is that it's now even statistically limited, the result. So if you think about the precision which we achieved, the precision on the di-quark mass coming from the Higgs, if it is in the booster topology, then you can correct for example, losing the neutrinos. So it gives you already, you know, a better result than if you couldn't do that. And the mass resolution, which we achieved due to our calorimeter being also very fine grained everywhere on the detector, unlike in the LHC, where, for example, we will see that also coming from CMS once we go to HL-LHC, but at least also having it in the central part of the detector where we have most of the events in our collisions gives us also there an additional edge in the mass resolution itself, that the mass resolution is also a lot better than it is at the LHC with the current detectors. So it's an improvement in the detector technology, and since we are statistically limited, that is the major factor at these energies. If you talk about these high energies, you're correct. If you consider the lower energies where the cross-section is significantly higher, there we get quite a bit using mu, for example, or C2EE.
Okay. Thank you. Also, I have another question actually. So are that technical showstoppers to go to the highest energy scheme? I mean, because it's not something that is straightforward, right?
I mean, there are technical challenges. At the highest energy stage, it is that our energy, from the theory which we have, it's financially possible. It's also possible to do it with the current technology. You cannot go far higher than 3 TeV. So 3 TeV is more or less the limit it was also said to be the limit, but is there, from a technical perspective, there is none, besides that the energy consumption which you will have will need to be updated. At CERN, at least, if you think about that. But I guess if we consider the upgrade of the infrastructure, no matter if you go, you know, for the linear colliders or if you go for the circular option, that also will need to be, you know, upgraded. So I think in terms of the technical challenge, that is clearly there, but it's not impossible to do it. It has been shown that it can be done with also with the backgrounds which you will have.
Okay, thank you.
So it's mainly the infrastructure which will need to be upgraded, but I'm pretty confident that that can be done.
But do you have estimates of the energy consumption of the different options for future colliders?
Yeah, at least it is done for Click, and I'm pretty sure also, you know, the colleagues from FCC did for sure do the same. I'm pretty confident about that. For sure, somebody can, you know, confirm.
Okay, thank you very much. So if there are no other questions, maybe we can move on to the next speaker, Mila. Or you need to stop sharing.
Okay.
So Mila will talk about CEPC.
Okay.
Go ahead.
Oh, I didn't start my video. Is it visible? Okay. Everything set? So my name is Mila Pandurovic. I come from Vinci Institute of Nuclear Sciences in Belgrade, Serbia. I'm going to tell you about the Higgs to WW decay in all jet final state at CEPC. So the CEPC is proposed future electron-positron collider to be built in China. It is a circular collider with foreseen circumference of 100 kilometers. Okay, it is primarily designed to be operating as a Higgs factory at center of mass energy 240 GeV with an integrated luminosity of 5.6 inverse afterburns. That will mean that foreseen 7 years of running time, that will amount to 100 million of Higgs events. Now, CEPC also foresees 2 electroweak runs. The first one is at Z-pole, 91.2 GeV, and the second one at WW production threshold, around 160, where the CEPC foresees a scan. Okay, so So, and for Z running time, corresponding to the Z production is 2 years, and for WW production is 1 year, which will amount to 100 billion of Z events and around 10 million of Ws. Now, CPC develops 2 detector concepts in parallel, and the main difference between these detector concepts is in the way they improve hadronic energy resolution in comparison to the classical calorimetry. So the baseline model, which is given on the left-hand side, is the CPC ILD, which is using the particle flow method. So this method relies on a highly granular calorimeter and in combination with the single detector measurement of, so let's say the charged particles are going to be measured by the tracker, an electromagnetic calorimeter, and only neutral particles are going to be measured by the hadronic calorimeter. So in this option, just to go over the detectors, sub-detectors, from inside out, we have a silicon pixel vector detector, and then a gaseous TPC, which is in the sandwich of inner and outer silicon tracker. After that, following the ECAL, which is tungsten silicon, and the HCAL, which currently is RPC, RPC glass steel. And after that, we're doing, of course, the tracking in the magnetic field of 3 Tesla, and we're finishing up with the muon detector, which is currently RPC. On the right-hand side, you see the other detector concept, CPC idea, which relies on dual readout calorimetry principle, which means that we're measuring the scintillating light and the Cherenkov light at the same time. And by combining that information, we can actually extract the electromagnetic part of the shower and in certain way combine them to achieve the higher hadronic energy resolution. More about this detector concept you can hear tomorrow morning. Now, at CPC, they did the reconstruction software. So on the basis of a CPC ILD detector model, which is following as a told particle flow method. So Arbor uses the simple property of the hadronic shower that it spreads like in a tree-like structure. So it starts from TPC hits, and then it builds up trees and forests, and at the end, at each tree is decomposed in the track segments at each branching, and then merge into tracks, which are then refitted. And the particle reconstruction for single particle efficiency, you can see in this table, and the achieved jet energy resolution is 3 to 4%. Of course, for simulation, CPC uses wizard event generator, which is interfaced with PITIA for hadronization and fragmentation. Now, the Higgs production at CPC is dominated by the Higgs production channel, which at 250 GeV amounts to 200 femtobars of the cross-section. And here you see the evolution of the cross-section of the dominant Higgs strong process with a subdominant WW fusion and a ZZ fusion, with, which have 1 order of magnitude lower cross-section in comparison to the Higgs Strong. And here are corresponding Feynman diagrams. And this Higgs Strong process is can be used at E plus E minus collider for the absolute coupling Higgs ZZ determination. And we do that using the recall mass method, which uses only the properties of Z boson decay to uncover the Higgs. So you see this distribution, which is obtained in ion mass of Higgs boson, which is obtained by the recall mass distribution, where the Z decays to a pair of muons. Also, at E plus E minus collider, we can determine the Higgs with high precision using several different methods. Now, the analysis that I'm presenting is fully hadronic Higgs to WW decay and Higgs Strong, which means that both W's decay hadronically as well as the Z from Higgs Strong. So we have 6 jet final state, which is the highest jet multiplicity at this energy. And the corresponding cross section is around 14 femtoband at this energy. So due to the nature of this Higgs Strong process, we have 6 central jets in the final state, which are very wide opening and potentially overlapping. And the goal of the analysis is to uncover the statistical potential of CPC for this type of measurement. And the analysis method that I use is based on multivariate analysis, practically BDT. And prior to that, I do the pre-selection, which you will see in next slides. The potential background given here and the evolution of the cross-section for the signal and for the background. We're mainly interested, of course, in purely hadronic final states because semi-leptonic and leptonic final states are easily removed in this kind of signal final state and at the level of pre-selection. Okay. So the most interesting background is a 2-fermion hadronic background, and because of its very high cross-section and pair of W's, which have the same signature as the signal, not same but similar. Okay, now we go to the event reconstruction. So prior to the analysis, of course, we do the event reconstruction. We use the KT algorithm with the optimized jet opening. And after that, I force events into 6 jets. Those jets are grouped to form the the real W and the virtual W boson. And of course, the WW pair is supposed to comprise the Higgs boson. And I use this chi-squared to choose my combination, the final combination, okay, which it has to be minimized, of course. Now, I come to the analysis. So for pre-selection is mainly targeted to use that high cross-section background to fermion. So I use several pre-selection variables. The first one is number of final state particles. And this distribution you can see here on the left, on the right plot for the signal given with black and for the background given with color. And for 2-fermion, which is given with light green, we can see a clear separation between signal and background. Let me just say that this is a shape comparison, of course, not the cross-section, not scaled to the cross-section. And the second and third variables are extracted from these plots. So you see this energy of the W, because this is a Monte Carlo information, or the reconstructed information energy of a W, real, versus the angle between reconstructed jets. And we see here that we have a slight hyperbolic dependency. And that also goes a bit for energy of a Z versus the angle between the jets. So this allows me to form a new variable, which is simply energy of a W boson multiplied by the theta, and the theta, as I said, is the angle between the jets. And the second one is the same, but for the Z boson. Here you see the distributions which are obtained as energy theta of the W boson versus the Z for the signal and for the relevant background. As you can see, we have a signal which is highly, let's say, localized here in comparison to the targeted 2-fermion background, which is scattered all over the space. So this allows me to form the set of cuts on these variables, which are given here. And the effect is here that we reduce this kind of background to the more than 2 orders of magnitude while preserving the majority of the signal. Now, about event selection, multivariate analysis are used, and I use several classes of sensitive variables. And in these types of final states, a D plus or minus collided or jet final state, the most important variables are coming, or those ones who explain the shape of the event, okay? So the most important one among them is a trust variable. And you see here, because we have six jet final state, we're expecting kind of isotropic distribution, that this is given with the black line given here, and not the similar ones for the background, which are leaned towards the higher values. Besides the trust, the most important variables are blackness and aplanarity of the event. And the second most important class of the event, of the sensitive variables are from the clustering level. And these are jet transitions. And this is a KT value at which the KT algorithm decides it should go from the certain number of events to the higher ones. So of course, because we have 6 jet final state, the most sensitive ones are when we go for 5 to 6 jet, or 6 or 7 jets. Again, this is shape comparison, and signal is given with black and corresponding background with the color again. Now, the last class of most important variables are the reconstructed boson masses. Of course, we use real W boson, DZ boson, and the Higgs boson masses. And here we have the distributions. This is the distribution of our signal. So this is 6 jet final state, reconstruction of the real W boson, DZ boson, and of course the Higgs boson, where we see the clear separation between the W and Z, which proves the capability of CPC to resolve that kind of jet final states. And just for comparison, I use this plot from CPC CDR. When you see the reconstruction of boson masses, but from di-jet final state plus missing energy of the lepton, where we see, so these are 3 different processes, di-jet processes, and this is our 6 jet final state. So on these plots,
you have 3 minutes left, Milan.
Yes, I will hurry. On these plots, you have the same distributions for invariant masses given for the signal given with black and a relevant background, and we can see that it's a good separation, especially for my invariant mass of the Z boson. And this brings me to my results. After combining all of this, I'll use the multivariate method with the preselection and optimize set of the final variables. And you see here the efficiencies, which are very high to the sub% level in the background deduction. Just to illustrate this, this is our signal and background. After the final selection, signal is given with black. So this brings me to my final result of this analysis, which is the relative statistical uncertainty of this measurement, Higgs WW in all jet final state in Higgs strong, of order of 1.7% with a signal efficiency of almost 30%. Okay, so this number had entered the global Higgs fit, and here we see the results of the measurement of various Higgs WW channels that were studied at CEPC at 250 GeV and their corresponding precision. And when we combine them, we obtain the statistical uncertainty of Higgs WW at CEPC of order 0.9%. I must say that in the meantime, they upgraded, that optimized the running energy to 240. So when we actually amount this to this energy, we arrive at 1% of relative statistical uncertainty for the W measurement. Now this brings me to my conclusion. CPCE is proposed electron-positron collider to be built in China. It is a circular collider with 100 kilometer circumference, and it's designed to be built as a Higgs factory primarily, but also foresees Z-pole running and W pair production. And all jet final state of Higgs WW and Higgs strong be studied, and it has been shown that the statistical potential of the CPC at 250 GeV is 1.7% using all jet final state. And the overall precision of all the channels which I studied at CPC is 0.9 at 250 GeV, which will amount to 1% at the 240 GeV of center mass energy. So thank you very much. And that's all.
Thank you very much, Mila, for your presentation.
Mm-hmm.
Questions? I can see Yazuyuki. Please go ahead.
Yeah, can you hear me?
Yes.
Okay, so I'm Yasuo Okumura from University of Tokyo for Atlas experiment. And I have a question about the efficiency. So you mentioned the 30% of efficiency in the presentation. And
yes.
what is the main reason for the loss of the 70%?
What is the main reason of the loss of the signal, right?
Yes, exactly.
Yes, because there is a high correlation between variables, right? There is no, first, there is no distinct variables because we have all jet final state that we can cut on. So we have to, and the variables that I used are moderately to highly correlated. That's why in order to reduce the background to the level, we have to lose this much percentage of our signal.
Is there some chance to improve this part?
Yes, but in order to improve this result, yes, there is a chance, but we have to go to on hit level to see the reconstruction, the clustering, and the jet pairing. So we have to go to the hit level, I think. I think that will help.
Yeah, thanks a lot.
You're welcome.
Other questions? So I have a question actually. Can you go back to the previous slide? You show some results, some expected precision using Z2LL, right? The previous one, yes.
Mm-hmm.
So it's better. You don't make a better job with Z2LL. This was one of my questions, and the side question is that you don't use the Z to calculate the Higgs mass, right? I mean, you don't use the
recall
out of S and Z to reconstruct the Higgs mass. Whereas when you use leptons, that's what is usually done, right?
Yes, that's the most important. Yes.
So my question was, what is the difference in mass resolution between those L plus L minus channel and the channel you are using?
Actually, that's a good question. I didn't calculate. I might take a look afterwards, but I'm not sure definitely. But definitely it's better with the leptonic primal plates.
Yes. And in this leptonic analysis, is the fit to the mass done or?
Yes.
Yes.
Well,
you use
one
only
of the most important variables, cut variables.
Okay, thank you. Any other question for Mila? You don't have comparisons to other future colliders in this plot, right? You have only to iterate.
You can see only to the LHC 300, and this is the CPC and a combination with high luminosity LHC, but not with other E plus and minus colliders.
So 1%, very nice. Huh?
Yes.
Okay, so if there are no other questions, anyway, you can also ask question. Yes, I forgot to tell this. Huh? You can also ask question if you have a technical problem. You can also have them on the Mattermost. Huh? But I don't see any questions, so we can move to the next speaker.
Okay, thank you.
Hello, can you hear me?
Yes, David.
Salut, Julie. So I'm going to share my slides. I have a poor connection, so I may stop my
okay
video if I see any problem. Okay, so I'd like to thank the ICHEP for inviting us, the FCC team, to present our Higgs measurements expected at this.
Can you put it to full screen or?
Am I not in full screen? Let me see.
No.
1 second. Now it's okay?
We still see the sidebar, but okay.
Yeah, I don't know how to do it right now. Let
it like that.
Let me stop sharing 1 second.
Okay.
Let me do it full screen first, and then no, but I cannot do it. Sorry, I cannot do it properly. Maybe here. No.
Okay, then it's fine. You can. I mean, it was okay. We could see the slide, no?
Okay. So first of all, let me go through a short introduction of why we are discussing at all the possibility to construct future machines. And the reason being is that we have many open issues in the standard model of particle physics. And let me list those motivations first. So in the first slide, you see that right now, although we have a successful theory of the elementary particles and their interactions, we don't know. We have not demonstrated that the Higgs Yukawa mechanism provides the mass to the lightest fermions. So UDS quarks, the electron and the neutrinos, we don't know how to couple to the Higgs because they are too light. So that's an open issue. The second one is that we don't know how the Higgs couples to itself. The Higgs trilinear and quartic self-couplings are not known. The fourth one is that right now we have a fine-tuning problem. The fact that the mass of the Higgs is so low compared to the next physics scale given by the Planck scale, and the fact that the Higgs is a scalar with running mass with energy means that you have 10 to the 16 orders of magnitude of fine-tuning between both scales, and this is a theoretical problem which is not statically. That points to some underlying reason to protect the Higgs mass from virtual corrections. And of course, there is the big elephant in the room, which is that the standard model only describes 4% of the universe, the visible fermions and bosons. We know that 20% of the universe is made of dark matter. We don't know what it is, but if it is massive, it should couple to the Higgs in some way. Now, the main reason why we are discussing that the construction of future colliders is that some or most of these open questions be answered at the LHC. And solving those fundamental problems in high energy physics requires new E plus E minus and PP colliders. And the FCC, the Future Circular Collider, that is being right now planned for CERN after the High-Lumi LHC. And we are right now preparing the feasibility studies and letters of intents to be completed by the next European strategy upgrade in 5 years. The idea is to construct a 100 kilometers ring to insert, first of all, a first E plus E minus phase, Higgs factory, and Z factory, electroweak factory. I will discuss this in my talk, but then followed by PP collisions at 100 TeV integrating up to 20 Mersatovar. Now, the topic of my talk is devoted to this say 8 years of operation of the E plus E minus machine to around the Higgs sector, so at the Higgs Tralum peak as well as the above that to look for the top coupling. And the FCC will allow to produce 1.3 million Higgs in these 8 years. And of course, the full FCC program includes 10 to the 12 Zs, 10 to the 8 Ws, and then 500,000 tops. So in slide 8, I remind you what the cross sections are. So basically, there are two main production mechanisms: Higgs Tralum and BBF, and the combination of both amounts to 250 femtovars, more or less. We'll be running at 240 for the Higgs Tralum peak, and then also at higher energies to look for the top Yukawa. And you see that we'll be producing 1.3 million Higgs in a very well-controlled environment with very small backgrounds and extra clean to carry the extra clean measurements. So with this more than 1 million Higgs, we can do very precise studies of the Higgs couplings, as well as looking for rare decays and BSM decays. And of course, we also have sensitivity to self-coupling and to the top Yukawa, indirectly through those virtual corrections that I showed there. Now, first topic, as I said at the beginning of my talk in the motivation, this is the typical plot of the coupling of the different elementary particles to the and then to the Higgs and the Yukawa value. And you see that we know that the Higgs that we have observed at the LHC couples to the heavy sector of the standard model as expected, but we don't know, and we won't be able to know what happens with the light sector. And that's a problem because the universe is made of the stable universe that we see is made of UD plus electrons, let alone neutrinos. And those couplings will not be accessible at the LHC. So the coupling to the Higgs, to the Higgs to the electron is the decay, as I will discuss next, is very, very small, so it cannot be observed at the LHC. And the idea that I will be discussing next is to produce the Higgs resonantly through E plus E minus, running at exactly at the Higgs mass pole, and then looking for an excess above the backgrounds. And then, of course, there is the open issue of the neutrino sector. How do neutrinos get their mass? In some way or another, they get their mass by coupling through the Higgs field. Of course, if neutrinos are direct particles, the coupling that you cover is tiny, 10 to the minus 12, but there are several motivations that through other sterile neutrinos, heavier, those could couple to the Higgs and mix with a normal active standard model neutrinos. I will be discussing those next. So first of all, the first discussion is this is something unique to the FCCE, is the possibility to dedicate a few years to run E plus and minus collisions at 125 from 000 GeV. So for this, we need to know the mass within MeV. And then, as I said before, the inverse decay, so the decay of Higgs 3 plus and minus is completely unobservable. You would need to produce 10 to the 10 Higgs. So even the high LC or FCCHH won't be able to see this on top of the huge Rallian. So the idea is to inverse the diagram and look for the E plus and minus going to Higgs. The cross-section is tiny, is 1.6 femtobarns. But of course, this assumes that there is no ISR, and this assumes that the beams are perfectly monochromatic. If you take into account that initial state radiation plus a beam energy spread of around the same size of the natural width of the Higgs boson, you see how the cross-section gets depleted. So you see those Laurentian peaks there, where you see the Born cross-section 1.6 and how it gets depleted when you adapt the ISR and reasonable values of the beam energy spread. So what we did, and we are still doing, is a study of 10 decay channels. You have them there in the diagrams on the middle right, and then on top of the backgrounds. And of course, the backgrounds that go through Z star and gamma star are huge, 100 to 10 to the 8 times larger than the signal. So you have to remove those with careful analysis. So the most significant channel so far in our study of all decays is Higgs to WW going to neutrino, sorry, lepton plus jets. And for this, with 10 inverse atomic, we expect a significance of 0.5. Now, if you add on top of this the 10 other channels, you can get around one sigma for 2 monochromatization working points that have been provided to us by the beam people, but the beam machine people. So all in all, it's a counting experiment. So you look for you count the number of events with a given final state, and you compare this to the predictions of background only or Higgs resonant production, and then from there you derive the coupling. So doing this exercise, we expect the preliminary upper limits at the standard model level by running with 4 interaction points 3 years. So this is very challenging, but it is already 100 times better or 3 times better than what the high LC or the FCCHH can do. That's the only chance we have to study the coupling of the Higgs to the electron. Now, the other topic I want to discuss is the Higgs coupling to neutrinos. If they are not direct particles and you have some kind of seesaw mechanisms where they mix with some heavier sterile neutrinos, you can have this type of processes here where you produce the massive, heavy, massive neutrino that then decays into Higgs plus a normal active standard model neutrino. And then the experimental signature is mono Higgs, where you see JJ, which is consistent with so 2 jets consistent with the Higgs plus missing energy from the neutrinos. And then using this final state, combining it with also the decays of Higgs to heavy neutrino and active neutrino, plus other electroweak precision observables, you can basically cover a very wide phase space in active external mixing and heavy material masses. Now, the second topic rapidly that I want to cover is the Higgs self-coupling. So we can constrain it indirectly at the FCCE by looking to the Higgs Tralum cross-section. So you see that this cross-section includes a small contribution that goes through loop diagrams where the self-coupling is involved. And it's a very small effect, as you can see, but it's visible at the FCC thanks to the excellent precision on the cross-section for the Higgs Tralum of 0.4%. And indirect limits on the trilinear coupling can be set at 40% level only using a Higgs Tralum and 20% combining also data at higher square root of S. Now let's move to the third topic. We have this problem of the hierarchy and naturalness, and this is a good motivation to look for BSM physics, which couples to the scalar set of the standard model. those. There are many BSM realizations that account for this: SUSY, composite Higgs, little Higgs. So the idea, if you go in an agnostic way, is to parameterize any BSM physics as an effective theory, and then you can work out a back-of-the-envelope formula that tells you that basically that you can set indirect constraints on new physics scale coupled to the Higgs sector by taking the ratio of 1 TeV over the square root of the precision of your coupling over 5%. So with this back of the envelope formula, that tells you that 5% deviations of the Higgs coupling with respect to the standard model, this is something that we can reach at the high lumiere LHC, will allow you to constrain a BSM physics that couples to the Higgs above 1 TeV. But if we go to 10 to the 6 Higgs at the FCCE, we'll be able to go up to 7 TeV. And let's see how we can do this. So you've seen this before in the previous talk by the other colleagues from CLICS, CPC. The key idea here is unique to a lepton collider, is to running at the Higgs Stralsund, is to study the Higgs independently of its decayed mode by looking at the wayside Z that decays into well-defined final states. So the high precision measurement of the Higgs Stralsund cross section with 1 million Higgs allow us to extract the GZ coupling within 0.2 per mil uncertainty. Then combining the decay of Higgs to ZZ with this GC coupling allows you to extract the total width to within 1%. And then, of course, you can do the same exercise for the rest of your covers, where you play with the production mechanism and the decay with the width determined from the HCC and ZH cross-section. And then from there, you determine the different UCAVAs. And you see here the type of final states. For example, you see here for the C going to dileptons, Higgs going to BB bar, Higgs going to tau tau, and so forth. Also, by measuring the recoil mass, you can measure the Higgs mass to within 5 to 8 MeV through the cleanest Z2 mu mu and in E channels. So with this is a summary of the Higgs couplings that are achievable at the FCCE. We expect 2 to 20 times improvement in the precision compared to high lumiere LHC expectations, which are 2 to 5% uncertainties. And you see the values there. The most precise one, the GCC coupling with 2 per mil uncertainty sets limit on the newest scalar couple physics at above 6 TeV. This is using this back of the envelope formula. But if you go to slide 17, you see that with a full EFT analysis, you see indeed that several effective field theory operators can be set limits above 6 TeV using the Higgs FCC data alone. If on top of this, you combine the Higgs plus the Z run, the C runs, so the electroweak precision observables, you can set limits in some operators up to the 100 TeV level or 40–50% in some others, depending on the type of assumptions. And then the last topic is the dark matter. As I said, if it couples to the Higgs, then we should see it by looking at invisible Higgs decay. That's what we are doing right now at the LHC, as you all know, by looking at BBF or associated. Yes, I'm finishing 2 slides. So looking at BBF, associated production, and so on. Here, the idea is to look at the Higgs Stralsund, where you measure the Z and nothing else. So the Higgs goes into invisible. So today, the limits of the invisible decay are set at the roughly 11% branching ratio. For the high lumiere LHC, we set 2%. And if you go to the FCCE, we will be able to set it to the 2 per mil limit, okay, by looking at Z going to charged dileptons and BB bar, and then looking for the missing mass in the recoil distribution. And also we can set limits on other exotic branching ratios, so final states that cannot be tagged as standard model decay, so multi-jets and so on and so forth. So with this type of limits on the invisible Higgs decay, we can eliminate a significant fraction of dark matter models, in particular dark matter models that are consistent, that provide a thermal relic abundance that is consistent with what we see today in the universe. So if the dark matter freeze out is dominated by resonant Z or Higgs chains, FCC will be able to test any such scenario of dark matter possibilities. So with this, I come to my summary. I hope I convinced you that the FCCE provides unparalleled luminosities in the 10 inverse autobarn range, running for about 8 years. In E plus A minus, at center of mass energy is between 125 and 150 GeV for ultra precise Higgs studies, down to 1.5, 1.7 per mil uncertainties for the most accurate coupling. This allows us to test the standard model couplings that will not be constrained at will not be accessible or constrained at the high lumi LHC, like the first generation UCAVAs or the self-coupling, and looking at the possible heavy massive neutrinos coupling to the Higgs, setting competitive dark matter limits that couple to the Higgs. And of course, with these 2 to 20 times more precise Higgs couplings than the high luminous LHC will push BSM limits scalar coupled to scales above 6 dB or 40 to 50 dB if we combine with the electroweak precision observables. That's all. Thank you.
Thank you very much, David, for this very comprehensive talk. So, questions? Uta, please go ahead.
Yeah, thank you, David, for the nice summary. What I found a little bit confusing is how many interaction regions are you now assuming? Because partially you were speaking about 5 inverse autobarn, 7 inverse autobarn, 10 inverse autobarn. Yeah, and there's obviously discussion of the 2 versus the very, very, let's say, complicated 4 interaction region option for FCCEE.
In principle, we were considering 2 originally, but now the possibility has been discussed to consider 4, and this will, of course, greatly improve the limits and the measurements that we can carry out. But in terms of couplings, you see there is 3, so it's basically 7 inverse autobarn, which is 3 plus 5, basically. So 7 at the 7 inverse autobarn, if I recall, at the Higgs Strahlung, and then 3 more at the at above that. So it's mostly BBF. Well, it's the tail of Higgs Strahlung plus then BBF.
No, but wait, is it now for 2 the nominal in the table or for 4? Because I think it's quite important. Because
if I recall well, it's 2.
Yeah, and as far as I see it, you don't consider any theory uncertainties, or you assume that at this time theory is solved, yeah?
Yes, of course. I mean, I discussed only the experimental measurements. Theory has to match the experimental precision, which is not today the case. There are improvements needed in many sectors, but the theories tell us that they will be able, by the time the FCC is ready to operate, they will be able to have reach theoretical uncertainties which are commensurate, if not smaller, than the experimental ones. I have to stress that often the statistical uncertainty is not the leading one. For some cases, it's a systematic one. So our goal also is to try to improve also there. So try to approach the systematic uncertainties to match the statistical ones. But of course, there is also work to do in the theoretical part. But I mean, basically you have to compute higher order corrections and QCD and electroweak corrections to different observables and reduce parametric uncertainties by measuring also different standard model parameters that enter into the calculations and so on and so forth. But this is under control in principle.
Fabio, do you have a question?
Yeah, hi David, thanks. It's very clear and nice presentation. I mean, I didn't know about these studies about the measurement of the couplings to the first generation. Of course, this would be by itself a very important result. Now, I guess here you have assumed 4 experiments. So my question is, well, 2 questions. First, how well you assume to know the mass has been measured, and the second is, I mean, do you have other potential physics measurements you can do when you sit the Higgs mass with your machine? Because if you have to stay there 4 years just for one measurement, my guess is that this will never happen, right? So.
Yes, so both are very relevant questions indeed. So right now we assume that we know the Higgs mass to within MeV. Right now the best direct measurements using direct reconstruction, we expect 5 MeV ballpark. So, but there are some ideas. I don't want to discuss them because we are testing them right now. There are some ideas to improve on this and maybe go below 5 MeV. So, okay, we are testing them. I don't want to comment on this. So we hope to be able to know the mass of the Higgs within a few MeV, so that of course when we run exactly at the peak of the resonance. Otherwise, as you see, this Lorentzian peak, I mean, as soon as you move off by a few MeV, you lose a significant fraction of the cross section. But then also you can play with ratios going to the running exactly slightly above, because running slightly above, you still are a little bit more free than below with respect to ISR, because I mean the electron and positron could radiate a photon, a few MeV photon, and then you're off the peak. But if you can run it slightly above, a few MeV above, and then play with different ratios, since you know very precisely the center of mass energy thanks to the transverse polarization of the beam at the FCCE, and thanks to the monochromatization, we know very, very well where we are running. So by taking ratios, we can do some tricks and try to improve this significance. All this is work in progress. It's a very tricky measurement. I mean, you can see in slide 10, we are looking at a signal of 80 counts on top of 27,000 counts. And so you see how tricky this is. And this is, okay, this is one of the channels. We have 10 more channels. We are trying to improve things in the analysis, but it's it's a very, very rare counting experiment. And then regarding the other thing, yes, you can do neutrino counting by running at 125. You can do studies of Higgs with ISR, so Z plus gamma. So yes, it is not just, I mean, if we run at 125, it is not just the physics program. It's not just centered into the electron you cover, but you can do other interesting measurements. So number of neutrino families, Z measurements with ISR, and so on.
Thank you.
Regarding this topic again, just for curiosity, and what about the BB? It's limited because it's overwhelmed by a irreducible background, or I mean, could it be improved eventually by detector design choices? I mean, dedicated choices. Or?
Yes. So Higgs to BBR, of course, is the leading decay channel, as you know. But we have. This is one of the 10 to the, I think it's 1 million, the signal over background here, because without cuts, because you have Higgs E plus and minus going to C star going to BB bar. And this is at least 1 million times larger. So you have to get rid of this continuum, and it's tricky. And at the end, we put it there into our significance calculation, but it adds very little. Right now, I think it's 0.1 sigma per 10 inverse attobar. So still, right now we are with one student. I put a link in slide 11. There is a poster by Andres Poldaro this coming Friday in the Higgs poster session. We are trying to improve this as we speak. Let's see how far we can get. The preliminary analysis that we did a few years ago and it's using multivariate analysis with neural networks and so on and so forth. And it's true that at the time, the performances that for B tagging and charm tagging and mis-ID and so on were a little bit worse. Now we know that we can improve them. So we may get something. The question is whether we will be able to adapt more significance to the final result.
Okay, thank you. I see that there is a question by Xinguo.
Hello, so this is Xinguo from Atlas. I have a question on the previous page. Can you comment on the dominant systematic uncertainties? Is this from the recoil?
Which slide are you asking about?
Page 10, yeah, just.
Oh, no, there is no, I don't know what you understand by recoil. What we do is, this is a counting experiment. So what we do is we run at 125.00 GeV, and we count the number of events of a given topology. Say that you are interested in BB bar events. So we count the number of E plus E minus going to BB bar. And we know that 1 out of a million of those events will have gone through the S-channel Higgs resonance, and that's what you're trying to you do a counting experiment. So you know what the cross section is for your background. this cross-section for the background is very well known. That's another assumption. There is no systematic uncertainty on the background uncertainty, because this will be perfectly known, hopefully, to within per million accuracy, if not better. And then you look on the excess coming from the S-channel resonant Higgs production. So you see how tricky this is. Does it answer your question?
Sort of. So what's the main systematic uncertainty? I still didn't.
No, I mean, maybe let's phrase it this way. My answer would be that the systematics is not important here. It's a statistical problem. The problem is that the signal counts are very small. So you take a look again at the most significant challenge right now, Higgs to WW going to lepton plus jets. You see that we expect 80 events on top of 27,000 after cuts. So here, systematic uncertainty is nothing. I mean, there is no systematic. You're just counting events. I don't know what you mean by systematic. There is no systematic. You just count the number of events. So here, it's the problem you have is that you deal with a very low statistical sample. So here, it's a purely statistical dominated uncertainty.
Okay.
So we should move on because we are running late. Thank you very much, David.
Thank you.
So let's move to the next speaker, Michele, for FCCHH. Can you share your slides, please?
Yes, I'm trying to find the Adobe Reader, but I don't see it in the, yeah, here it is. You guys see the slides?
Yes, go ahead.
Okay, so I'm going to give a short review of the possibilities in doing Higgs measurements at the FCCHH. So the FCC project doesn't need much introduction. This was given extensively by David before. I will just say that the FCCHH is a potential second step after any plus and minus collider at CERN. This would be a 100 TeV collider in the 100-kilometer tunnel. This would require 16 Tesla magnets. Within the context of the European strategies, other options have been briefly studied, the energy LHC, the low energy FCC. These are all options that would lead to high energy PP collision in shorter amount of time, but I will not discuss them here. And you can see, you can find references for all of these options in the European strategy documents and in the various CDRs which were published for the preparation of the European strategy. So why would we bother in measuring Higgs at the FCCHH? After all, there will most likely be any plus or minus machine before the FCCHH, and we all know that if we want to make precision measurements, the plus or minus machines are much better because they provide cleaner environment. However, if you look at this table that I'm showing here on the right, I compare the possible reach in precision for the main Higgs couplings, both at the high luminosity LHC and at the FCCEE. You can see that the FCCEE, which I take as a benchmark for reach of lepton colliders, the FCCEE shines whenever, as long as the Higgs, the statistics are large, right? So as you know, as David told you before, there will be 1 million Higgs produced at the FCCEE. And in fact, this is how, this is for the very abundant channels, this is where you see that you can get highest precision. However, you can see that for the rare decay channels, you quickly run out of steam. So for example, X2 mu mu, X2 gamma gamma, and the Higgs self-coupling, which you can only study via radiative corrections. This is true as well for the high luminosity LHC, which will provide some kind of precision measurements for this value, but it won't reach the percent level precision. So this is a motivation enough to go to higher energy, where you can benefit from the increase in the cross section, and where the FCCHH would really make a difference is with the Higgs self-coupling, the top Yukawa, the Higgs to invisible, and the Higgs rare decays. There is something else you can do, because you can actually benefit from the fact that with the Higgs mass recoil measurement, you have an absolute measurement of the X2ZZ coupling. If you actually measure ratios of branching ratio at the FCCHH, this allows you to get rid of several systematic uncertainties which concern the production and some of the objects. If the object efficiencies are the same in the numerator and denominator, you can actually measure ratios of branching ratio, or equivalently ratios of couplings, which if you know this value, for example, for X2ZZ from FCCE, which you know at the per mil level. This gives you an absolute measurement of the value on the numerator if you're able to measure this kind of ratio at the FCC-HH. So more generally, what you can benefit from at the FCC-HH is very large production rates, so 20 to 60 time cross-section with respect to luminosity to the LHC, so which gives access to very rare decay modes. Something else which is pretty interesting is that you now have access to a large dynamic range for Higgs production. That means that you can do differential measurement both in the large PT Higgs, so in the very boosted regime, or in high invariant mass with the Higgs plus X, or X in the final state could be V or Z or whatever. This gives you opportunity to reduce some of the systematic uncertainty, or at least place yourselves in the region where the systematic uncertainties are smaller, and also to develop indirect sensitivity to some beyond the standard model effects which appear at large Q square. And of course, the high energy reach also gives you opportunity to use the Higgs as a tool for studying BSM, but this is something that I don't have time to discuss much here. Now, single Higgs production, the production modes at the FCC-HH are very much the same as the LHC. As you can see, going from 13 to 100 TeV gives you a very large boost in the cross-section. The one that benefits the most is, of course, TTH, because this is the one that requires the highest Q square in terms of energy in the center of mass, where you get a boost of a factor of 55 in the production rate. So this gives you 20 billion Higgs producers at the FCC-HH, which give you a factor 10 to 50 in the cross-section. So very naively, if you have a measurement which is statistically limited at the FCCE or at the Illumina LHC, you expect a factor 10 reduction in statistical uncertainty. This is kind of the rule of thumb. And as I said before, the large statistics also allows you to place yourselves in a region where you have cleaner samples, lower systematics, lower impact of pileup, and so on. Some just considerations on the kinematics. So if you consider the inclusive production, so the Higgs production at threshold, something to note is that if you go to 100 TeV, but you look at the same Q square, you have a larger dynamic range in terms of possible imbalance in the parton from the protons. So this means that you will produce standard model physics, and in particular Higgs, at a larger rapidity. So in this plot, you can see in the bottom, you can see the Higgs 2,4 lepton. The most forward lepton peaks at higher rapidity, and this is even more evident in the vector boson fusion, where the most forward jet in the VBF is going to peak at 4.5, whereas, as you might know very well, at the LHC, this peaks around 3. So this has implications on the way you will instrument your detectors if you are going after these kind of signatures. As I said, there is also the opportunity to study the Higgs at very large PT. If you think about it, you can see that you have 10 to the 6, so 1 million Higgs is produced with a PT larger than 1 TeV. You have also interesting things that happen where, if you look at very high PT, you're more probably producing a Higgs coming from TTH, for example, than VBF or gluon fusion. And of course, studying Higgs at high PT gives you interesting opportunity in terms of studying the effects of new physics, because of course, if you look at the PT spectrum, or let's say here is the integrated PT spectrum, this is very much sensitive to whatever you put in this loop. And as you can see this in this, even in the EFT approximation, where you go use the top mass to infinity. You send the top mass to infinity. And again, you now are able to study the Higgs in a new dynamical regime at very high PT. And this also has implications in terms of designing detectors. You want to have highly granular detectors. So now going to the measurements, I of course cannot discuss everything. I will discuss a selected number of measurements. The top Yukawa measurements is one of them you can do. Of course, you can do this at the Illumina HC, where you know that you can reach precision of order 2 to 3%. What you can do here, and what you can also do at the Illumina HC actually, is study the ratio of the process TTH over TTZ. You see that the production mechanism is very much the same, that the final state is very similar, which means that if you measure this ratio, you will have several systematics which will cancel out. Now, this ratio is actually proportional to the Yukawa coupling, to the Higgs to B bit, which you can get from FCCE, and to the TTZ, which you can also get from FCCE. So if you are able to measure this ratio to 1%, this gives you basically a Yukawa measurement of the level of 1%. What you can do is study this in the boosted regime. This allows you to remove some of the systematic, of the combinatorial backgrounds. You still have very large background from TTBB and TT bar plus jets, but at least at the statistical level, you are able to disentangle this contribution. And of course, by measuring TTH and TTC simultaneously, you can see the double peak. You measure the ratio of them, and you can actually get rid of several systematics. So one thing that could be done here is also explore, for example, the T tau tau final state, which could give a similar sensitivity here. And this is something which we did not study yet. So the Higgs rare decays, I call rare Higgs to gamma gamma, ZZ2/4L, mu mu, and Z gamma in the dileptonic final state. Now, this is a very naive analysis, which goes beyond the consideration that if you go to very large PT, you're actually reducing systematics uncertainty. You're also more confident in your detector simulation because you are less sensitive to pile up. And in fact, your object efficiency at very large PT gets smaller. Imagine you will have plenty of highly boosted Drellian events from which you can measure these efficiencies in data. And in fact, you can actually measure this by looking at X2 for lepton, Higgs to mu mu. And in fact, if you can measure the ratio of these two, you can see that depending on which kind of assumption you have, if you're statistically only or with some kind of conservative or optimistic assumption on the systematic, where partially this cancelled because they enter a similar kinematic regime, cinematic range in PT, or you can measure this ratio, for example, at the level of 1%. And as I said at the beginning, this measurement, of course, can benefit from a X to ZZ coupling measured at the FCCE with a precision of 1%. So you can actually indirectly infer now the Higgs to mu mu coupling at the level of 1%. This is something you cannot do at the FCCE. Higgs to mu mu, as I said at the beginning, is measured at the level of 10% because you only have 1 million events. Now, these are other ideas that exploit similar, this similar philosophy where you can measure WH over WZ in various final states. I won't discuss this. These are just studies that were done at Parton level, but these show that these kind of ratios can be measured at the level of 1%. Other studies that can be done in single Higgs, which we did not study yet, and these are interesting, of course, are exclusive decay channels, X2, J, psi gamma, omega gamma, rho gamma, etc. Now, of course, X pair production is one of the flagship measurements of the FCCHH. The measurements follow very much the same philosophy as at the LHC. You have the same production modes, the dominant one being gluon fusion here, that is almost 1 order of magnitude larger than VBF, TTH, and VHH. These measurements, of course, is relying both on the fact that you can measure the rate of the Higgs, but you can of the di-Higgs production, but you also have to measure the slope of this production rate, which gives you the sensitivity. Of course, if you had a very much larger slope here, you would have more sensitivity on the Higgs of coupling. In fact, one of the variables that allows you to measure, to have sensitivity on the self-coupling is, of course, the di-Higgs invariant mass. And this you can see from these two diagrams here. If you go to very large invariant mass, you're going to suppress the contribution of the S-channel diagram, whereas if you go to very small di-Higgs invariant mass, you're going to enhance it, or at least if you go in the region of close to the Higgs pole mass. So this means that this variable gives you some shape sensitivity on the Higgs self-coupling. And of course, the rate is what is important here. This measurement gives you a precision at the level of 50% at high luminosity HC. So just if you make a naive scaling from 100 TV to 14, you get a factor 40 from the total rate. You get another factor 10 if you assume 30 inverse autobahn for the total integrated luminosity at FCCHH. So you expect an order 20% in precision. Of course, this is if this measurement would be totally statistically dominated. We studied the 4 main channels that contribute here, which are, yes, I should manage. We studied the 4 main channels that contribute to the sensitivity of the self-coupling, the BB gamma gamma, BB tau tau. So the BBZZ is a very clean channel. This is something which is very new compared to the LHC, where you have barely one event, whereas here you start to open up it, but it's you have very few events also at the FCCHH, but it gives you a very clean measurement, so it contributes to the final sensitivity, and of course the 4B final state. Here I'm showing the likelihood scan for the signal strength here for BB gamma gamma and BB tau tau, what we do is we have the dashed line, which is the statistical uncertainty only, and we studied 3 different scenarios where, of course, one corresponds to a very optimistic scenario of systematic uncertainty, and then the medium and the very loose, let's say, very pessimistic scenario. We also performed the combination here. I won't discuss the details here, but the bands are this the difference between the scenario optimistic and pessimistic, which I was discussing before. What we get at the end of the day is, for the optimistic scenario, a 3% precision. For a more conservative scenario, we get order of 5.5%. This, of course, assumes standard model coupling. In particular, it assumes that we know the top Yukawa to very high precision. We also made a scan assuming all standard model coupling as a function of k lambda. Of course, what you see here is that the precision actually blows up. It blows up exactly in the region where the cross-section flattens out. And we also studied the expected precision as function of the integrated luminosity, which tells you that, okay, with the full integrated luminosity, you get order 3 to 4%, whereas you can actually reach already to 10% with only 2 inverse autobahn, which corresponds to 2 years of running, 2.5 years of running at the FCCHH. I just want to mention finally these very nice measurements. So this is a pheno-based measurements, but it's nevertheless very interesting, which is the measurement of the C2V coupling, so the VHH coupling in the VBF di-Higgs channel. So this is a measurement that is performed also at the LHC. And the consideration here is, again, is if you go and study this physics channel at a very large invariant mass, you're going to suppress this, and you have this very nice cancellation that gives you very good sensitivity to the C2V coupling. In fact, if you actually know the CV, which is basically X to WW or X to ZZ, this you know to better than 1% precision at the FCCE, you can actually convert this measurement into a C2V coupling, and you see that you can actually measure this to the level of 1%, at least statistically. So this leads me to the conclusion. I hope I convinced you that very large statistics at the FCCHH, of the order of 10 to the 10 Higgs boson, open up a whole new range of possibilities, in particular on rare decay channels. And this is really complementary to the FCCE. We can measure ratios of coupling or equivalently ratios of branching ratio that allows us to cancel systematic uncertainty, which between the numerator and the denominator, which give, again, order 1% on some of these rare couplings, namely X2 mu mu. The Higgs self-coupling can be measured with a precision of 3 to 5%, depending on how conservative you are on the systematic uncertainties. And of course, there are many more interesting studies to be done in the realm of Higgs physics, which I did not discuss here. And I think this will be for thought and for future studies. Thank you for your attention.
Thank you very much. Okay, so questions for FCCHH? So while waiting for people to raise hand, I will ask my questions. So I was wondering for TTH, I was expecting gamma gamma and even maybe ZZ with these high statistics to be dominant. Of course, here you cancel the systematic with TTZ, but maybe with gamma gamma you don't need to do such a thing.
Right.
So
of course, if you were to do a standard measurement where you measure the plane production and decay into gamma gamma, you will get a better measurement than if you do it into X2BB because of systematics which are more under control. You have 2 photons in the final state. The problem is, as you say, that you cannot cancel them out. So of course this has to be studied, but at the end of the day, you are measuring an absolute rate which will be limited by luminosity uncertainty and theory uncertainties at the end of the day. So if you cannot measure your luminosity better than 1%, you will not measure this better than 1%.
Whereas I was wondering if you did the study at all for
no,
gamma.
I did not. We did not do it at all.
Yes. Okay. And besides this, I have a question on HH. So this is the flagship measurement, right?
Yes.
Regarding Higgs. So I guess, would this channel drive the detector design? And
right. So this is an excellent question. Yeah. Well, it doesn't drive it so much more than it drives it than Higgs physics or plane Higgs physics drives the detector at the at the LHC. Of course, the BB gamma gamma requires an excellent diphoton invariant mass resolution, very much like the Higgs to gamma gamma at the LHC. And of course, this requires to have a electromagnetic calorimeter that provide you with a good resolution. On the other hand, you are in a kinematic regime which is not so much extreme. So I would say that for most of these objects in the final state, the LHC type of experiments would provide the necessary performance in terms of object identification. Of course, this is without talking about pileup, which will be as high as 1000 DFCCHH, at least in the high luminosity run. And this, of course, will require, picosecond level timing precision and this kind of stuff, which, of course, we assume here that it's going to be a solved problem by then. But in terms of, pure resolution and, identification capabilities.
Bit tagging can be important also, I guess. And maybe
bit tagging is extremely important.
But,
BB
mass resolution, I mean, if it was better.
Yes, right. This is going to be driven by your tracker resolution and by your, how well you have an impact parameter resolution. So indeed, this will drive it, yes, of course.
So is there any other question? I don't see anyone raising hands. So maybe we should move on because we are late actually. This is I apologize for this. So Uta? Great. So please go ahead. So Uta will talk about LHEC. We cannot see your slides. Ah, yes. And FCC-EH.
Can you hear me?
Yes.
Okay, very good. So thank you and good afternoon. I'd like to show some selected measurements, how we can do precision Higgs physics in electron-proton collisions. The good news is we have the proton beam already there. This is a high LUMI Large Hadron Collider where we have 70 eV protons, or as outlined by Michele, we may have the FCCHH. And if we add a 9 kilometer structure, I hope you can see my laser pointer, then we can construct a genuine twin collider. So we can construct genuine proton-proton and electron-proton facilities which run simultaneously. This is a sustainable option really to use best our high energy smashers. Electron-proton collisions will then run exactly at the same time when the proton-proton is running. So is it for 10 years and we have 10 years data taking? For FCC, we expect like 20 years data taking, and this determines somehow the current numbers of assumed collected integrated luminosities. We have no pileup conditions. Yeah, this is like 0.1 pileup event expected at the LHC with a center of mass energy at 1.3 TeV, or at the FCCH of 3.5 TeV. So these are click energies, yeah, 3.5 TeV. There are more talks by Bernhard Holzer and also about the energy recovery, LINAC in particular, in the next days as well. So what's the signature? What's the difference now between all the E plus E minus and the PP that we just heard? So we have the protons, which are either the LHC protons or the FCC protons, and we have our energy recovery LINAC delivering 60 GeV highly polarized electrons. And then you see immediately that the dominant part is really the vector boson fusion, where we have the WW vertex producing a Higgs boson with a missing energy and a forward jet. Or you have in the neutral current case, you have a final state electron, and you test immediately event by event, either the WW Higgs or the ZZ Higgs vertex, which is quite unique. Here are in the lower table are the charge current, so the WWH and the ZZH cross-section for the LHEC and for the FCCH. And you see that assuming the highly polarized beam, we can get cross sections as high as 1 picobarn, which is higher than one could expect at click. The theory is very well under control because it's all vector boson fusion. Yeah, and again, since electron-proton collisions are unique to determine the proton structure, to unreveal this, as shown yesterday by the talk by Claire, we have everything determined in a self-consistent way. So we do not have to worry about any alpha S or PDF uncertainties. Our analysis framework and detector, it's in this sense quite standard. We have the MATGRAPH 5, where we can put in standard modular BSM production cross-section. And then we have the fragmentation hadronization by Pythia 6. And then we usually tested fast detector simulations by Delphis to test out. This is by far not finished yet. And so there's, of course, still room for a lot of improvements. And we tested a single to background analysis, either CATS-based or using boosted decision trees. So just a word on the deep inelastic scattering kinematics. Yeah, again, here's our Higgs production in electron-proton collisions, where we either have the WW Higgs or the ZZ Higgs, just decided by the final state. On the upper corner here, right corner, I put the kinematic plane in dependence of the Bjorken X and of the let's say, produced mass of the particles. And you see the big yellow range, the full yellow range. This was a Hera-EP collider. And then you see the blue. This would be the leaping forward of electron-proton collisions at the energy frontier. And if you would go to the FCC, then we would get another like factor 100 beyond the Hera-EP collider. In the diagram below here, you see, again, this is a dominant neutral current cross-section. Yeah, this is like our standard process, which we measure. Then you see that all the three production, yeah, like E plus, E minus, EP, and PP are belonging together. Yeah, it's just the direction where you look at this graph. And this, I think, it's really a very, very important message that we should keep in our minds, that each of those production modes have their place to live. Now you may be wondering, because I'm speaking about 60 GeV electrons smashing of either 7 TeV or even 50 TeV protons. So this is an extreme asymmetric configuration. And so what I'm illustrating here, and here you see the pseudo rapidity eta of the full range. And then you see in the middle, you see in red, yeah, you see this is a produced Higgs particle. And if we assume, like also Michele was indicating, that for the FCC energies, and this is determined by the proton energies, we need something like pseudo rapidity ranges up to 6. Yeah, so we see exactly the same as Michele was showing, that the forward quark, which is a green line, it's very forward. So we need these detector acceptance. But you see also that the scattered lepton is very well contained. This is this light blue, and that's the Higgs decay particles really following the Higgs, and this is going very central. And this unique features that we have rapidity gaps between all these decay particles, and then we have the difference in the azimuth. This is exactly what we will use, and which will make this so nice to analyze Higgs events in electron-proton collisions. Here are, on this slide, are some rates and the geometric acceptances. And this is for the LHEC with the center of mass energy at 1.3 and FCCEH at 3.5. We see here the assumed luminosities, again, dominated by the assumed lifetime of the proton-proton machines. And we see here the number of expected events, and we can get like 1 million Higgs events in BB bar for the FCCH, for instance. We also see on the right-hand side that within the assumed acceptance of such a detector, so we are not to be worried about. So we really have very nice acceptance. Yeah, if we assume, for instance, a B tagging up to 3 or 3.5 in pseudo rapidity, we have something like a 70% acceptance for the LHEC and around 55% for an FCCH. So this asymmetric configuration is not too worrisome. So we did a lot of Higgs studies already, even before the Higgs was discovered, and this was cut-based. And here you see just a list of samples and, let's say, quite simple-minded, naive assumptions, standard assumption about flat bead tagging with some very, very conservative rates for misidentification. And you see in the lower plots, in the lower left-hand side, you see clearly a peak of the Higgs, and you see clearly a peak of a Z. And this is just plain, really rather simple kinematic cuts. And you see this also for the LHEC. And these are plots just without assuming any polarization and just for 1 year of data taking at such high energy electron proton colliders. So this is pretty good news. So what we did then further, we started really to do also to use more boosted decision trees, so really to loosen the kinematic cuts. And this is visualized here in this invariant mass distribution, where you see here with a black points and where this blue circle is, that we have staggered in the most pessimistic way all our backgrounds. And then even without any bead tagging, we see already an Higgs peak just due to these unique kinematic signatures. Then we applied the heavy flavor tagging. And then as a third step, we made a boosted decision tree in the search window. So, and just to give you a flavor that what we tried to do, and these are perhaps quite complex plots, but this is just that we have always the interplay between what we are assuming for our detector resolution, for the impact vertex resolution, and what we are doing in the analysis. And this means, since we have B jets here for Higgs to BBB or Higgs to charm in the lower plot in the finite states, we have the interplay between those two. And you see in the lower plot, you see the full agenda of the blue, red, and whatever points. You see the variation of the jet parameters within an anti-KT R parameter of 0.5 to 0.9. And then we also assume different values for the impact parameter resolution within 10 micrometers, 5 micrometers if we halve this, or if we double this. And then we see that the Higgs to BB bar is really robust with respect to the boosted decision tree cut. We see some high number of selected events. And for the charm, of course, for the Higgs to charm, we are much more sensitive to the impact vertex resolution. But if we are going to, let's say, a sensitive anti-KT choice and let's say a good resolution of around 10 micrometer, then we have a quite nice result. And this is what we then are showing here. This is on the upper plot for the Higgs to BB bar with the remaining backgrounds, where I put here a long explanation of all justification of our assumptions, because the cross sections are so similar for the LHEC to 240 GeV plus and minus colliders, so that I could really very, very nicely benchmark the results. And similarly for the Higgs to charm. And if we do this with our certain assumptions that we understand in the usual way via control region, our backgrounds, then we expect a single strength of 0.8% for the Higgs to BB bar and 7.4% for the Higgs to charm. For in electron proton collider, it's a high LUMI LHC. Then we did a separate study, because this is something really, really nice, is that if we have the WW production, and this is what here in the blue box is. We have the WW producing the Higgs, and the Higgs is decaying to WW. This should give us very naively direct access to the WW coupling, because this is just simply speaking, if there's no new physics, this is 1/4 of the single strength. And this is where we did for the most asymmetric configuration for the FCCEH, a study where the full jet for jet decay, and this is a cross section of 100 inverse femtobarn, and this is what we pass to some version of our FCC Delphis detector. And then we again made studies of the various anti-KTR choices, and we were only considering resolved cases that all 4 jets are reconstructed. And then you can see here—
You have 3 minutes left.
Hmm?
You have 3 minutes left.
Okay, then you see here on the right-hand side, you see in the red line, and this is truth matched the Higgs peak, and you see the W peak, and you see the off W star, and you see this then also with the combinatorics. And here, and this is really the difference, that we are not doing any combinatorics assuming masses. We just do this using the kinematic features. And then we can get that only with this one channel, we get a Higgs to WW coupling in the range of 0.5% uncertainty, which is a quite unique result among all these Higgs factories. This slide is showing the summary of all the Higgs single strengths, where we see again for the WW Higgs and the ZZ Higgs for various EP collider configurations, and the amazing things that we can reach very, very nice precision by the combination of all those. We can also test then also electroweak theory in the usual way. And what is more interesting is that we can have, of course, then the standalone EP kappa coupling fits, where we see that for the various configurations, assuming various proton energies, coupled with the energy recovery, then that we get extremely good precision. Yeah, this is really a clean environment and also a precision facility. This is from our FCC study, which is very nice because here we have also the FCC-EH. And you see the main thing, it's really the complementarity between the Higgs to ZZ from an FCC-E and the Higgs to WW from an FCC-EP. And this is really the spirit of the future circular collider and of all this combination, that we combine those. And this is illustrated best in this plot, because usually people are speaking about the combination of EE and HH. But there are correlations, and these are these blue lines where I put the crosses, but the crosses only vanish if we add electron-proton collision. Electron-proton collision, and this is on the right-hand plot, there will resolve those correlations and then reduce this future, reduces these further correlations. So that this Higgs production in the three collider modes, EE, EP, and PP, they are important to resolve this correlation and are important for the theory developments. This is one slide which you can digest. This is the option if we would have this in the 30s. LHEC would add charm to high Lumi LHC, and I put here the 1%. It would put with the big blue lines mainly all basic couplings below 1%, and we would have this extremely nice, this is this red thing here, extremely nice knowledge of our proton Higgs cross section. I have there more detailed numbers in the backup slide that you can really digest the improvement, and also for the luminosity measurement, for instance, for an FCC-HH, because then one could do Z counting and would have less than 1% luminosity uncertainty for FCC-H, to answer Michele's question. Yeah, this is my summary. Thank you for listening. Yeah, so that Higgs measurements in EP are self-consistent experimentally and theoretically, because we have this DS cross sections with very small systematic uncertainties. We have the striking synergies. Yeah, if you have the EP at the energy frontier and EE colliders, and of course our high Lumi LHC, so that this energy frontier electron-proton would really open up a new world also for our proton-proton searches. Yeah, with the reach of, so there are many, many more talks that we have here. It's this conference. And so there's really, really a very, very nice synergy that it's awaiting just to be explored. Thank you.
Thank you very much for this very nice talk. So questions for Uta? So I can't see anyone raising hands yet. So maybe I missed it, but so the implication of the PDF knowledge and alpha S on the HL LHC measurement, did you show a plot? Maybe I missed it, or?
Yeah, the plot is here, but better is if I'm going to my backup. This is, can you see this?
Yes.
Because this is just only for the high Lumi LHC. If we would really have a twin collider, which is still in reach in the 30s. And then you would see in the lower table, and this is in this our CDR update, which should appear on the archive either today or tomorrow. And then you see all the proton-proton, this is all what you know, the proton-proton cross-sections, and you see the PDF and alpha S uncertainties. And then you see this is the current, with the high Lumi LHC PDF, the expectation. And then you see it's all below 0.5% if you would have LHEC, PDF, and alpha S 2 per mil, including alpha S. So this would be a big leap forward. And similarly, you would see this then also for kappa W, for instance, which we would get to 0.5%, or kappa Z. So we could get already, we could get a huge improvement. And this LHC PDF, this would also transfer directly to our luminosity measurements, for instance, with Z counting, which I'm also involved in with Atlas. We could have luminosity determined for proton-proton collider to better than 1%, in the range of 0.5%. It would be mainly the scale uncertainties of the Dorian cross-section. So this would be amazing, amazing prospects. These expecting this extension also in our limits. It would give us another TV in our limits, and our direct limits. So it's really amazing.
Yes, it's very nice to see the complementarity also between them.
Exactly. This is really the complementarity to really have this external input that frees our proton-proton to do what we are best, for the searches and for the rare decays and etc.
So other questions for Ita? Yes. Cinco?
So I will ask one. So for the pileup conditions, how does the pileup conditions in LHEC compare to the LHC?
There is no pileup. LHEC has this, and this is where we were using quite different methods, like with a total gamma p cross section to get an estimate, and we always end up with something like 0.1 event. So
okay, wow.
There's no pileup. There's no pileup for LHEC.
Thanks.
Yeah, welcome.
Okay, so I don't see any other questions, so we can move on. Thank you very much, Ita.
Thank you. I stop sharing immediately. Wait.
And Sean?
Yes, thank you.
Can you put it to full screen, please?
Yes.
Great.
Thank you.
So you can start.
Good afternoon in Europe, good evening in Asia, and good morning in America. Today, I'm going to present our results for flavor-changing neutral Higgs interactions involving a top decaying into a charm and a Higgs boson, followed by the Higgs decaying into a pair of taus. The taus will decay into leptons, including electron and muon. In the standard model, the T to CH branching fraction is very small. So any discovery of this channel will be a hint of new physics, either a tree-level flavor-changing interaction or enhanced loop interactions. Top is still the most massive elementary particle. Used to be the Z as the runner-up. Now our mass giver Higgs is the runner-up. So we consider two Higgs double models, and my favorite is a special Higgs model for the top quark. In this model, top is the only elementary fermion coupling to a second doublet we call phi2, and all the other elementary fermions coupled to phi1. Since all experimental data agree with the standard model, so maybe we can simplify our consideration of physics, of new physics in the Higgs basis. This special top Higgs doublet model involves flavor changing neutral Higgs interactions as well as CP violation. But I'm going to use a general 2 Higgs Doppler model, not just the special model for the top. If we consider Higgs potential in the Higgs basis, phi 1 mimics our beloved standard model Higgs doublet, and phi 2 is something new. Tangent beta is not well defined if we don't have a Z2 symmetry. And beta minus alpha is not well defined either. It's just the mixing angle between the Higgs basis and the physical mass basis of the neutral Higgs bosons. Here we show that tangent beta can be expressed in terms of the Higgs couplings. We follow the conventions of Haber and Davidson, and as well as Stahl and collaborators. So we have kappa and rho. Kappa is diagonal and fixed by fermion mass. It's exactly the same as the standard model Yukawa couplings. And rho is everything new. Again, let me remind you, cosine beta minus alpha is just for comparison with models with Z2 symmetries. The rho matrix has both diagonal and off-diagonal elements. Off-diagonal elements will lead to flavor-changing couplings. Since MH is 125, MT is 173, we have two complementary processes. One is T to CH. The coupling is proportional to cosine beta minus alpha. Another channel is heavy states, either a heavy scalar or a pseudo-scalar decaying into TC bar plus T bar C. It is proportional to sine beta minus alpha. In the alignment limit or the decoupling limit, cosine beta minus alpha is approaching 0 and sine is approaching 1. So these two are complementary. We learned from George Ho that if there is a light Higgs lighter than the top, then we can have appreciable branching fraction. And we calculate the total width as gamma T to BW plus gamma T to CH. The branching fraction of T to CH is just gamma T to CH over the total. We learned from Atlas with several channels that the branching fraction should be less than 0.11%. That translates into an effective coupling of 0.064. For many years, most theorists used Trincher ansatz as the benchmark, that is about 0.09. So Atlas has done us a favor, that is, we know that the effective coupling must be less than the conventional symmetric geometric mean of the Trincher ansatz. That is square root of MT MC over V. So we will focus on T to CH, H to tau tau. And this is in collaboration with Phil Gutierrez and Rishabh Jain. In our study, we have used a model set up by Kaoru Hagiwara and his collaborators called tau decay in MATGRAPH 5. This will increase the statistics significantly. So we use that to study the tau decay. We feed events into Pythia 8, and we also use Delphs to simulate detector, and we analyze with root. In addition, we also use parton level analysis, and we improve our root analysis with binary decision trees. We require that the leptons from tau decay will have a momentum fraction between 0 and 1. In a paper that I'm going to mention by Chen and Xia, they suggested another useful kinematic variable called centrality. And I will show you the comparison of momentum fraction and centrality. If we require physical momentum fraction, actually it requires a large centrality that is positive. So these are recent studies. Chen and Xia considered both lepton-lepton, lepton-hadron, and hadron-hadron. Atlas considered BB bar, tau-tau, WW, ZZ for multi-channel, and gamma-gamma. So Atlas set a limit that is 0.064 for this flavor changing neutral coupling, neutral Higgs coupling. And in our study, we followed a nice suggestion by Mark Scher, Jing Jiang, and Tao Han. Tao Han and collaborators suggested in T2CH, the charm energy in the top rest frame can provide a distinguishing power between signal and background. We have used collinear approximation, means the taus in Higgs decay, they are highly boosted. So the decaying products are in the same direction as the tau. Therefore, we can use missing transverse energy and the visible leptons or lepton and tau hadrons to reconstruct the tau momenta. And with this approximation, we can see pronounced peak in M tau tau for MH and MC tau tau for MT. The dominant background is TT-JZ, and we can tell them apart very well if we apply a mass window near MH or near MT. When we consider events with missing transverse energy, we usually also consider a transverse mass. But we are going to show that the collinear mass actually is much more powerful. After M tau tau and MC tau tau cut, the effect of transverse mass is negligible in this case, but it provides a good confirmation that there is some resonance decaying into visible particles plus invisible particles that show up as missing transverse energy. This is the E charm, that is the charm energy in the top rest frame. We can see even with event generations in Delft's output with root analysis, T2CH, in T2CH, that the charm energy in the top rest frame has a pronounced peak around 41.4. And the energy from the dominant background TT-JZ is very different. Okay, now let's come to centrality. For Atlas collaborators, I want to ask you that, or remind you that your definition of centrality in the ICHEP 2019 paper is different from the Chen and Xia paper. Your definition of centrality is symmetric. If we follow Chen and Xia definition, we can see that the distribution, the centrality distribution of the Higgs signal is in green and blue. It is very different from the background from TT-JZ. Chen and Xia suggested we could apply a cut by requiring centrality to be positive. So in this figure, I hope you can see clearly, green is from C tau tau without X cut. If we require the momentum fraction of leptons or lepton and the tau hadron to be between 0 and 1, then you can see that the TC tau tau after X cut will be this blue curve. And you can see that effectively requiring X between 0 and 1 is similar to requiring centrality greater than 1.0. And for the dominant background TTJJ.
You have 3 minutes left.
Pardon me?
It's just to let you know that you have 3 minutes left.
Oh, thank you, thank you. So the black dash curve is TTJJ before X cut. After the red curve is TTJJ after X cut. Again, you can see the same behavior that after X cut, that's the momentum fraction cut. It is similar to a centrality cut greater than 1. So that removes a lot of background. So this slide shows the cross-section for the Atlas limit. These are cross-section in femtobarn for 13, 14, and 27 TeV collider energy. And the dominant backgrounds we have considered are TTJJ, BBJJ tau tau, BBJJ WW, and other processes. We require every event has 1 tech B, 3 jets. One of them should be able to reconstruct the top mass we treated as the charm, and 2 light jets that will reconstruct MW, and B jet should reconstruct MT. Sometimes when we apply too much cuts, we have very few events. So we have to use Poisson distribution. And we learned from Cowan et al. That we can simplify Poisson distribution significance with this definition. If NB, the number of background events, is much greater than NS, then it recovers the Gaussian significance. So this is a figure to show we have used binary decision trees to improve our significance. And for lambda equal to 0.64 with 100 inverse femtobarn, cut-based would give us 0.24 a significance, but BDT can improve it to 0.7. This is quite striking to me. This is a summary for tau tau channel. This is for 5 sigma. For 13 TeV with 139 inverse femtobarn, we can reach to 1.4 times 10 to the negative 3 in branch refraction, and lambda TCH will be about 0.073. You may say this is larger than Atlas limit. That's right, because this is 1 channel with 5 sigma requirement. Atlas limit is many channels with 2 sigma requirement. So for 3000 inverse femtobarn, we can reach to lambda TCH 0.33, for 14 TeV 0.031, for 27 0.023, with corresponding branch fractions next to it. For WW has a similar final state if we consider leptons. This is not as striking as tau tau. So we combine them together later. But for this one, I want to show you that it's not too bad. We can combine with tau tau to improve overall significance. Around the time of Higgs discovery, when we knew that MH is 125, we did a study of H2BB bar that has the largest branch fraction. Then a CMS physicist, Kaifeng Chen, reminded us ZZ is the Higgs discovery channel. It may be promising to see T to CH to ZZ. So we wrote another paper, And recently, Rishabh, my student, and I did WW, and this presentation, we focus on tau-tau, and we combine them together. So this is T to CH to C tau-tau and CWW star. So you can see the red is the significance at 13 TeV or 14, slightly higher in the near future when we have 160 inverse femtobarn. So red is WW. Magenta is the significance for tau-tau. If we combine them with simple quadrature, then we have the green curve. So we can reach 5 sigma at a coupling that is approximately 0.038. Okay, let me summarize. Okay, if we can see T to CH or H to TC bar, this could be an extension of the Higgs sector, and this could be a signal beyond the standard model. In the alignment limit, cosine beta minus alpha is approaching 0, so T to CH becomes challenging. Fortunately, heavy states, heavy scalar and pseudo-scalar decaying into TC bar plus T bar C can be sustained by sine beta minus alpha approaching 1, and could be, the event rate could be appreciable. And I want to thank my collaborators, my colleague Phil Gutierrez, an Atlas member, and my student Rishabh Jain. He's going to be a postdoc in Taiwan at the National Taiwan University. Thank you.
Thank you. So we are running late, but maybe we have time for one small question, like quick question. Stefania?
Yes, hello. This is Stefania Gori from UC Santa Cruz. So since in the last slide you mentioned the heavy Higgs going to top charm, yeah, I wonder if there are studies or if you've thought a little bit about that, and especially in the context that for the heavy Higgs you could have its production also in association with the top charm, with the top and the charm, if you have this floor changing coupling. So I wonder what are the prospects there, if you have studied that, or if...
Thank you for asking. George Ho and I, along with our postdocs, we did this a couple of years ago, and we found that if rho TC can be as close to 1, that is lambda TC is also close to 1, rho T, yes, then this could be the only 2 dominating channels. That is, one is heavy scalar and pseudo scalar decaying into TT bar, or T to C bar, or plus T bar C. So we found this is very interesting because we can reconstruct the Higgs mass pretty well. If we consider T decays to BW, assuming W is real from the lepton and missing transverse energy, we can reconstruct the Z component of the neutrino. And we have 2 solutions. We choose the better fit, and we can reconstruct MH and MA. So this channel, we encourage our Atlas and CMS colleagues to search for this decay. And thank you for asking.
Okay. Thank you. So let's move to the next speaker.
Hi.
Hi, Juan.
Okay.
Okay.
So I start sharing, right?
Yes, please.
Okay. Okay. Here we go. first of all, thank you very much for giving me the chance to present this work done in collaboration with Fernando Alvarado and Adolfo Guevara. This is a quick outline of the talk. Well, first, I will discuss some results on bounds on new physics scales that seems to push the new physics scales well over the TeV, over 10 TeV, 20 TeV, and other bounds that seems to allow seem to allow still resonances in the few TeV. In the second part, I will just discuss a simple scenario, a simple model where that naturally suppresses standard model Fermi interactions and puts these things together. And finally, essentially the conclusions will be that there is still it's perfectly possible to have new physics states at the 1-2 TeV, even in spite of the bounds. So let me show you the typical bounds on resonance masses. Here is one of the typical diboson searches, one of the most stringent ones, where little by little the masses of these resonances that became to dibosons have been pushed farther and farther, here over 4 TeV. But I would like to notice. Sorry, I would like to notice that, for instance, although this contains all the possible production channels, including the vector boson scattering, this type of searches, essentially, once you dig out a little bit in detail, you see that essentially what they are testing is this production channel. Is quark anti-quark production of the resonance, and then this decaying into the diboson, into the two bosons. A similar type of searches would be the four fermion interactions, the look of contact four fermion interactions. Already from lab times, one could find, well, it was found that the scales suppressing these four fermion effective operators were in many cases over the 10, 20 TeVs, and similar, as I said, there are similar bounds from LEP, Tevatron, LHC, and also in low energy hadronic experiments. So, which seems to point out that these four fermion operators are very suppressed, and that the new physics scale should be at very high energies. While on the other hand, other analyses like the electroweak precision test allow for resonances in the few TeV, like the ones showing you here, in more restricted scenarios where you have where you impose high energy constraints, ultraviolet completions similar to those in Technicolor. Then you still have place. You can still have place for resonances in the 4 or 5 TeV, but at the moment that you release this very stringent constraint and you go to scenarios where you only have one Weinbergson rule, like in working Technicolor, then these bounds on the masses of the resonances immediately get looser, and you can even have masses in the 1.5, 2 TeV range. Okay, and here you have similar analysis of of the low energy constant related to the S parameter compared to the mass of the lightest spin 1 resonance. You can see more on this tomorrow on Ignacio Rosé's talk. And a similar thing happens with if one looks at a little bit more in detail in vector boson scattering and Young production of diboson resonances. In the few TeV range. In principle, if one looks for resonances in the 1 to 3 TeV, what has been found is that LHC clearly is not yet sensitive. However, this is not because the resonances are not there, but because the cross sections that are typically associated with masses with resonances in the with vector resonances in those ranges are typically below the femtobarn. Okay, and in addition, if you add further up the efficiencies, you can see that the cross sections drop even further. So, however, if you look at these works, you can see that still there's hope, because even if you have resonances in the 1, 2 TeV, they might be seen in the long term if one reaches, for instance, 3 inverse octobarns, and one is lucky with the properties of the resonances that they have widths of the order of 40, at least 40 GeV or larger. Okay, so how can one put these two things together? Having 4 fermion operators very suppressed, and these masses of the resonances pushed well over the 4 TeV, and on the other hand, how is possible that in vector boson scattering on the reject production one has or in S and T analysis one can have resonances in the few TeV range. So a simple scenario that solves this problem, a simple solution, is found to be motivated by the Drellian analysis by Katai, Isidore, and Kamenik that look at this type of productions. Where the standard model fermions were coupled to the resonances, to these vector resonances, only through the electroweak gauge bosons. So in this work with Adolfo Guevara and Fernando Alvarado, what we had a look at what was the impact on the whole low energy effective field theory rather than particular cross sections. What was the impact if there was no direct interaction between the new physics sector and the standard model fermions? So let me just sketch a little bit the setup in this quick transparency. Essentially, the setup is the following. One has resonances, hopefully at the TeV or higher, and at low energies we have the standard model content. The Higgs effective field theory, the low energy Higgs effective field theory, is built based on on symmetries. In particular, a basic symmetry is custodial symmetry and the electroweak symmetry breaking pattern from this chiral symmetry into custodial. And in addition, if one goes to higher energies, one adds resonances following keeping the same symmetry pattern, and in addition to have some predictivity, one is often forced to use some multivariate completion hypothesis, like the Weinberg rules I was referring before. And then the game consists on adding all the possible resonances that you may couple consistently with following this symmetry pattern. And this would be what you have at high energies, and then if you go to low energies, then you get a low energy effective field theory containing the standard model degrees of freedom and having this custodial symmetry and the symmetries that you use to build your theory. At low energies, one is going to have a low energy chiral expansion where the leading contributions which will be order p squared, the first correction order to p to the 4, order p to the 6, etc., etc. Having inducing an expansion in the observables in the same way, where the first correction would behave like p squared, where the leading term would behave like order p squared, the first correction like p4, p6, etc. Where p here stands by any soft scale. Typically is covariant derivatives and soft momenta, but it can be also masses. Okay, if one is in the low energy range. And if you want to, finally, I think I didn't type it here, but if you want to see more on this, again, go to the talk of Ignacio Rosell and Carlos Quezada tomorrow Thursday, 30. construction of the Higgs effective field theory. And what is the impact of this? And then going back to our particular scenario, what is the impact of this resonance gauge boson mixing in the Higgs effective field theory? So we'll have a Lagrangian at high energies in the resonance region, where one has a piece with no resonances, with only light degrees of freedom. The standard model degrees of freedom are contained here, and then also some resonant interactions of this form, with a kinetic term, the mass term, and then the interaction of the resonance with the standard model degrees of freedom. Where here the key point is that this interaction is only with the bosonic degrees of freedom of the standard model. So here you can see the particular form in the case of a spin 1 vector resonance, where the resonance is coupled to the electroweak gauge boson field strengths, and also to the Goldstone bosons, or longitudinal electroweak gauge bosons, if you prefer, in the unitary gauge, and also interactions with the symmetry allows for interactions with the Higgs and the Goldstone boson. You can see that the interaction with the Goldstone boson always needs these derivatives. Okay, so it means that at low energies, attitude, the Goldstone boson interaction goes to zero if the momentum of the Goldstone boson goes to zero. And similar construction can be made with for the axial vector bosons. And the typical way of obtaining the low energy effective field theory consists, and integrating out the heavy degrees of freedom, consists of extracting the equations of motion of the heavy degree of freedom, the resonance, okay, obtaining the classical solution for the resonance, and then you substitute the resonance field by this classical solution. Okay, the classical solution will be a function of the light degrees of freedom, in such a way that once you do this substitution, since you have substituted the heavy degree of freedom by a functional of the light degrees of freedom by the bosons, then you are going to have that this object here, this Lagrangian, this high energy Lagrangian after the substitution, only depends on the light degrees of freedom. Okay. However, this is still a non.
3 minutes left.
Sorry.
You have 3 minutes left.
Okay, thank you. However, this object is still non-local, as one might expect. However, when you go to very low energies, when you make a low energy expansion, you find that this Lagrangian has an expansion in terms of local operators, where you have a leading order term, order p square, and order p4 term, order p6, and so on. At order p square, one does not obtain at tree level any contribution from the resonances, and what all you get is this term that eventually also contains the standard model and possible deviations also at this order. At order p to the 4, one obtains a typical correction of the form 1 over the mass of the resonance times the product of chi-r, okay, of light degrees of freedom, bosonic degrees of freedom, and suppressed by 1 over m squared. But here, first thing one notices is that there are no fermionic operators at this order, and in addition, there are no custodial breaking operators. If you go to order p to the 6, then you have one additional suppression by 1 over mr squared. So in global is suppressed by 1 over mr to the 4. One has one more derivative, and at order p to the 6, one gets many more terms, many more operators in addition to those that were obtained at order p to the 4. But the interesting thing is that due to this resonance gauge boson mixing, some of the terms that appear at order p to the 6 have this particular structure, derivative of field strength, derivative of field strength. And if one remembers the equation of motion of the gauge fields, one can see that this derivative of gauge fields can be of gauge field strengths can be traded off by by fermion bilinear currents. Okay, and in this way, effectively, what happens is that two of these derivatives that one has in this order P26, two of these P's become masses. Okay, and in addition, one has the appearance, one obtains of 4 fermion operators. Okay, however, even if they have the structure of order P to the 4 operators, they still have the suppression of order P to 6 operators. Okay, so diagrammatically it would be something like this. In principle, you could have interactions like this. At low energies, this becomes a point, but this goes like P to the 4, okay, times F, the coupling, the mixing FR square. But since here you have 1 over P square and a 1 over P square of the gauge boson propagators, at the end of the day, you end up with, even if this looks like a non-local object, it has some local contributions that look at low energies like 4 fermion operators, and that have typically this type of suppression. If you do a little bit some numbers and you look for these operators, 4 fermion operators, and you compare it with the typical bounds, for instance, this is one of the most stringent bounds that gives lambdas of over 20 TeV. What you find, I'm about to end, so in case chairwoman gets nervous. What you get is that the suppression that you obtain, instead, if you take our result, instead of being just simply suppressed by 1 over m squared, it's suppressed by 1 over m to the 4 times a particular combination of p square scales. Okay, well, I remember that p stands for any soft scale of the theory, so it's masses of the Z, masses of the W, and even combination factors of V. Okay, which are all of the typical of the same order. In addition, if one uses the 2 Wembersham rules, the contribution of axial vector and vectors combine in some specific values. And if you impose these bounds now, since this factor that one has here multiplies this simple suppression 1 over mv squared, even if the suppression of the operators seems to be very large, 20 TeV, when you look at the numbers and the bounds on the masses of the vector, one can see that in the case when the mass of the axial vector and the vector is very degenerate, one can get some reasonable bound of 1.9 TeV, but at the moment that you allow for some more natural splitting, not so tight degeneracy, then these bounds get much looser, and then they drop below the TeV. So essentially, you get almost nothing. On the other hand, a similar result, other type of contribution that one obtains from this other P2-6 operator after using the equation of motion of the gauge boson fields is that there are contributions to the custodial breaking oblique parameter T. But again, instead of being suppressed by 1 over mv squared, as it happens for this parameter, which is related to the W3B correlator, the T parameter is again suppressed by 1 over mv to the 4. Okay, and in practice, this means that this T is very small, and in practice for the analysis is like having it essentially 0. And if you go to the experimental data, what you find is that depending on the splitting, you may have bounds of order 4 TeV, or even lower at the moment that you allow for some more natural splitting between the vector and axial vector resonances that can get down up to a few TeV. And I also indicate that here there are no loops, so all this is at 3 levels. So this just gives you an idea of around the value, what values you will be moving. So essentially, the message is an optimistic message, or tries to be an optimistic message, where new physics could be just around the corner. This is okay with the bosonic measurements. It just needs the proper suppression of the resonance, of the coupling of the resonance and the fermions. a pattern that that fits these structures is, as I said, the standard model fermions coupled to the standard model bosons, and are those that connect the fermions with the new physics. And this scenario is helped with the Higgs effective theory and the chiral expansion seem to solve this issue. And thus resonances in the 1,2 TeV are, as I said, perfectly allowed, as one actually sees. One can see when you do analysis of vector boson scattering and the oblique parameters I was referring, and LHC searches, as I said, in WW scattering, the cross sections will be naturally small, and so it will be difficult to find, and it will require time. For fermion operators searches, sometimes called compositeness searches, are not really that wouldn't be not really that sensitive in the sense that the scale that is suppressing the operator is not really the scale of new physics, but is a much more complicated combination. And on the other hand, low energy searches, what low energy means here, electroweak scale or lower, can be more fruitful since they and one can look for deviations in low energy bosonic electroweak precision observables. It could be, maybe it could be better. I truly not sure. Could be better. Clearly, there is place to improve, to experimentally improve, as it has been seen in the prospects of the different future facilities. But again, as I said, this would be also a long-term project, so it will require time. So thank you very much. Really sorry for the extra time taken.
Thank you, Juan. So are there questions, quick questions, because we are very late?
I'm sorry.
So thanks for this optimistic message, but nevertheless,
thanks.
So
I disconnect.
Is there hope, at least on the very long term, at ICHEP to see something? Or?
Yeah, sorry, I'm trying. Yes. Okay, I disconnect. Stop video and silence.
Okay, so let's move on to the next speaker. Last speaker of the session. We can't hear you. You're muted. Oh.
Oh, yeah, sorry.
We can hear you.
So, hello, everybody. My name is Alexey Kachanovic, and I would like to present our recent paper, which was published this spring, and which we write together with my colleague Ulrich Niersta and Ivan Nishanjic from Karlsruhe Institute of Technology. So it's not full screen. So plan of my talk is following. First, I would like to provide motivation why in general Higgs decay is interesting, why we interested in this particular process, and why we decide to recalculate some well-known process. And then I would like to provide some detail about our calculation. And after I discuss some result, and finally I provide conclusion. So, and I think I don't need to talk much about motivation why Higgs decay are interesting. And I can say only that deviation between experiment and theory can provide some hint for new physics, and it's very important to study Higgs decays and standard model, and very important to obtain good precision in prediction. And why we interested in this particular process? Because, for example, Higgs decay in 2 lepton provides lower branches fraction Y for light leptons, of course. Why? Just because all these processes is proportional. All this diagram in this process proportional to Yukawa, and higher order always has correction to Yukawa. But in process, when we have extra photon, it is possible to couple two left lepton. So it's a flip possible. And for electron, for example, decay when Higgs decay into to electron 3 level is completely negligible if compared with one loop level. And for muon, this is the same order. It's like 3 times smaller than decay into to lepton. Why we interested? Why we recalculated this process? Because there are a couple of papers, and only 2 papers provide analytic result, and with one result we completely disagree. And all others paper provides only numerics, and this numerics with different cuts, and we decide to produce a result which can be used very easily for implementation, different inputs and cuts. So we generated this diagram with fine arts, and there are 2 3-level diagram and around 100 one-loop diagrams, which we divided into certain classes. It's simply a topological dividing, and we also have diagrams is, for example, 2 classes of diagram. We divided between this propagator, which is not with loop momentum. For example, one class is with gamma here, and second class with Z here. One of our goals was to check gauge dependence and find some classes which gauge dependent, and except of some trivial subclasses, there is no classes which independently gauge independent. And we need to sum up all contribution to obtain gauge independent result. So for evaluation of these diagrams, we use it FineCalc. For some analytical check, we use it package checks, which connected to FineCalc via add-on fine helpers. Gauge parameters which we have in this calculation are corresponding to propagator of photon, Z propagator, and W propagator. For constellation Xi A and Xi Z, it's enough only sum up all diagrams, and it's cancel straightforward. To cancel Xi W, we need to substitute this condition. We need to express one mass in terms of another one, for example, MW or MZ. And this provides restriction for parameters which we use. And for example, in our calculation, it's fine structure. Inverse of fine structure is fixed as 132 instead of 128, more familiar. And nevertheless, some diagrams are UV divergent. Total sum of all contribution is UV and are infrared convergent. So, and one more comment which is not mentioned here. So we keep masses of top quark, mass of Higgs, mass W and Z, and all others masses we neglected. We set to 0. General Wald structure has also antisymmetric tensor here, but and in some work it appears, but what we obtained, it's only pure symmetric part contribute toward structure, and we searching for source of this extra antisymmetric part, and there are two possible sources. One diagrams with fermion loop and Z propagator without internal momentum. And there are two diagrams, and these diagrams indeed produce this epsilon tensor, but it's cancelled out from if sum up these diagrams. Second possible source, it's a box diagram where there are a contribution with 3 gamma matrices in the matrix element, but after summation of all contribution from loop diagram, we found out that there is no contribution with 3 gamma matrices. So we didn't find any source of this extra epsilon antisymmetric epsilon tensor. And Vart structure is very convenient for calculation, because need to extract only 2 coefficients, for example, A1 and B1, and A2 and B2, it's obtained by symmetry very easily. And for to avoid divergent in Z-pole, we use Bright-Wigner propagator, and to cross-check, we also calculated in complex mass scheme, but all result in our paper provides with Bright-Wigner approximation. So here finally comes the result, and this is our result with solid black line, and we digitalize it plot here. Sorry, differential decay rate for 2 electron with respect to invariant the electron mass, and we took with the same cut result with these 2 papers and compare, and we found out that there is discrepancies between these 2 results, and that was one of our motivation. You can see here in peak where is biggest contribution, pretty nice. This line's pretty nice coincide, but here it's a large slope, and it's very hard to say how good our result agrees. And here differential decay rate with respect to the muon mass, and you can see if for electron we completely ignore 3-level contribution here, 3-level contribution starts play a role. And for low energies, total contribution almost repeat the shape of one loop contribution, but starting from, let's say, 100 GeV, 3-level plays dominant role. We also calculated this process for in respect of invariant mass of lepton and photon pair, and here we can see opposite behavior, that 3-level plays a role with low energy, and with growing energy shape, total line shape is repeating one loop contribution. Another goal of our paper to calculate forward-backward asymmetry with respect of angle between lepton and photon. This is definition of our what we call forward-backward asymmetry. Here you can see a result for electron and for muon, and explanation why it's very close. For electron, 3-level plays completely no role, And for muon, it also very small. And you can see on this plot, only this part is different between electron and muon. For electron, it's completely out of here, and for muon, it's present. And one loop is the same, just because we ignore lepton masses, and process on loop level for electron and for muon looks completely the same. So, and finally, you can see my conclusions. First, we require more analysis to understand discrepancies between different approach and different papers. Here you can see again numbers which I previously provides, and one more conclusion, that it's important to have all diagrams, and we cannot neglect, for example, boxes if you want to have a gauge independent result. For standard gauges, it could be not so big difference, but for some exotic gauges, it's really can play a big role. Thank you very much for attention.
Thanks very much for this nice talk. Questions? Spira, please go ahead.
Okay. Can you go back to slide number 7?
Yes.
For these discrepancies, I observed that you have a kink at about MEE equals 40 GeV that the Passarino calculation does not seem to have. What is the reason for this kink?
Good question. Good question. We also figure out that in one paper present this kink, and in a Passarino there is no this kink, and we believe that this is some numerical problem.
Mm-hmm.
So we don't know sure, but we believe that this is some numerical problem.
Does it mean that the kink is not real?
Yes, we believe that this is not real. So,
may I add with some other short question concerning the choice of the fine structure constant?
Yes.
A different slide where you mentioned this 1/132. Can you distinguish the Z boson vertex from the photon vertex? Because usually if you have an on-shell photon, then usually you are using the fine structure constant in the Thomson limit.
So this limitation comes from condition of gauge cancellation. So this cosine theta Weinberg, it's expressed like 1 minus mw over mz.
Yeah.
And then we use this definition in a finite structure constant. So, and we have like 3 parameter and 2 equation, and we can choose 2 of them, and sort is fixed. Like we can say finite structure is different, but then we need to follow this equation and set mass of W, not for example, a mass of Z, not from actual measurement.
But did you try to trace the photon vertex? If the photon vertex can be defined in the Thomson limit and all the rest with this 1/132. I think it's important to get the proper matching to Higgs to gamma gamma for small invariant masses of the fermion and interfermion pairs.
Yes, I try to understand your question. I'm not precisely sure that I understand.
So this means if you're going to small invariant masses of your charged lepton pair, then
yes,
of course you are you are approaching the region of photon conversion.
Mm-hmm.
Off-shell photon converted into a charged lepton pair. And then of course you are much closer to Higgs to gamma gamma, where the in this because for this process the natural choice is to choose alpha in the Thomson limit, because you have on-shell photons.
So unfortunately, we cannot choose this alpha. It's fixed by satisfaction of gauge condition. So and we believe that possible to obtain more familiar alpha like 100 inverse like 128 with higher order correction and with running this coupling, and we don't provide any running.
Yeah, but this also means that a low energy limit like QED does not exist automatically in your calculation.
For low limit we use CAT.
I think it is because this is a conceptual problem. Therefore, I'm asking.
Okay, so maybe this can be followed up offline.
Yeah.
Or on the MasterMost channel. Or also in the room will stay open for discussions after the last session, because we are very late. Sorry. So there will be just a 5 minutes break with the next session, which was supposed to start 4 minutes ago. So let's come back in 5 minutes.
So if anyone wants to still test screen sharing or audio, you are welcome during these 5 minutes.
Hi, Thomas, can you hear me?
Yes, hi.
I'm presenting the next talk, so if you don't mind, I just check the screen sharing.
Sure, go ahead.
Okay, can you see
perfect.
the screen?
That's perfect, yeah.
Okay, and also I'll check if the video works because my connection from home is maybe not the best.
Well, if you encounter a problem, you can stop video.
Yes, so can you see me as well?
I need to click somewhere. Yes, I can.
All right. Maybe I just stop sharing in case someone else wants to check sharing.
Okay, thanks.
Okay, I think it's time to start. So I'm Stefania Gori from UC Santa Cruz, and I will be chairing this session. So Anna, if you could share your slides. Okay, so an invitation to all the speakers, please be on time. And I will tell you when you have 5 minutes, and apologize if I interrupt you for a second. So the first talk is by Anna Boreka-Bielska on rare electron flavor violating Higgs decays. Thank you.
All right, I hope you can see the slides. And okay, so I'm going to talk about the searches for rare and lepton flavor violating decays of the Higgs boson with the ATLAS detector. So the motivation for these searches is that we can probe the GABA interactions in the standard model, and we can test the yet unobserved Higgs boson couplings to first and second generation fermions, and also test the BSM models that allow for lepton flavor violation, which is forbidden in the standard model. In this plot, you can see the Higgs coupling to different fermions and bosons. As a function of particle mass, you can see that all—
Anna, sorry, we cannot see you. It doesn't really matter, but just wanted to mention that we cannot see you.
Okay, let me try something. Okay, I hope.
Okay, great. Now I can see you. Okay, go ahead.
All right. So you can see that all results from ATLAS detector are nicely aligned with the standard model Higgs boson prediction. And you can also see that the coupling to muons is still constrained with the limited precision comparing to the other results. So today in this talk, I'm going to cover the brand new Higgs to mu result with full run-to data, and Higgs to EE and lepton flavor violating Higgs to mu with full run-to data, and lepton flavor violating decays with the E tau and mu tau final states with partial run-to data. Okay, starting with the Higgs to mu. Here we have very small branching ratio of the order of 10 to the -4. And we have to deal with a large irreducible background. And in the top plot, you can see the mu distribution with all the backgrounds. So you can see that we are dominated by the Drellian background. And we have some smaller contributions from the boson top. And we expect a signal to background ratio of an order of 2 per mil in the signal region. As for the analysis strategy, we apply a loose selection to maximize signal acceptance. We add up to 1 FSR photon to improve the mass resolution. And in the bottom plot, you can see the mass distribution for 5% of signal events, where we find an FSR photon at the reconstruction level, before the recovery in black and after the recovery in blue. And you can see that there is a significant improvement for these events. So after FSR recovery, we have a production-driven categorization where we target TTH, VH, VBF, and GGF production modes using boosted decision trees. And we extract the signal from signal to plus background fit to the muon mass in the mass range from 110 to 160 GeV. Starting with the categorization, so in each category, we target the leptonic or semi-leptonic decays of the TT bar pair, and we require at least 1 additional lepton and at least 1 BJet. We use the BDT discriminant to further reduce the background. And in the on the left-hand side, you can see the mass distribution in the TTH category, and you can see that the highest contributions from the backgrounds we have are from the TT bar and TTZ processes. We expect the signal yield of 1.2 events in this category and signal to background ratio of 8%. Now in the VH categories, we target leptonic decays of the vector boson. So it is either W decaying to lepton and neutrino or Z decaying to lepton pair. And we require at least 1 additional lepton and no BJets. We perform a separate training of the BDTs in this 3 lepton and 4 lepton channel. And we define 2 categories in 3-lepton channel and single category in 4-lepton channel. And you can see the mass distributions in the middle. The 2 in the middle are for 3-lepton channels, and the one on the right is for the 4-lepton channel. And you can see that the backgrounds are dominated by the boson, but in the 3-lepton channel, we have small contributions from the Drelian and top. And here we expect the signal yields ranging from 0.5 to 2.8 events, and signal to background ratios ranging from 0.8% to 3.7%. Now moving on to VBF and GDF categories. So here we require events with exactly 2 opposite sign muons and no BJets. And we divide events into N-jet channels with 0, 1, and 2 or more jets. And we perform separate training of the classifiers in different channels to fully exploit the difference between the signal and background. And in the 2-jet channel, we have a special dedicated VBF BDT classifier. And we categorize events based on this output, its output into 4 VBF categories, which you can see in this top plot here. So we define these 4 categories, and then events that fail this selection are considered for GGF categories in the 2-jet channel. And so we have in each N-jet channel, we have 4 categories in the GGF production based on a dedicated GGF classifier output. And here in this plot, you can see this output for the 2-jet category, where we, as I said, find 4 categories. So in this plot, you can see in the top panel the signal over square root of background, signal to background ratio, and the background yields. In the middle panel, the signal composition, and in the lower panel, background composition in categories. And as you can see, we have a very good separation of the production modes. We obtained wide range of the signal to background ratios, which are ranging from 1 per mil to 20%. And every category that we defined contributes in 0.1 and 0.6 sigma. Now, the signal model is a dotted crystal ball. And for the background model, as I said, we expect a very low signal to background ratio. And so we need an excellent way to constrain the background. And we tested our model on high statistics fast simulation of the main background, so of the DIAN. And this background model is created as a product of 2 components. So we have a core function and an empirical function. And the score function is a leading order Drelian line shape, which is convolved with a Gaussian to account for resolution effects. And this is a fully rigid function. And so it has no free parameters, and same in all categories. And empirical functions corrects for distortions in the mass shape induced by the selection of each category. And it is selected based on a number of criteria from the 2 families of functions that I listed in this table. And it has a number of free parameters, but it depends on the category. In this plot, you can see the fit to a fast simulation in the VBF high category. You can see that the top panel, the background only fit, empirical function in the middle panel, and standard model signal prediction in the lower panel. That brings me to the result. Here in this plot, you can see the combined fit to the weighted mass distribution. We observed the signal strength of 1.2 plus or minus 0.6. We're still statistically dominated, and the main systematics are coming from signal theory, then signal experimental systematics, and the background modeling. And in this plot, in this lower plot, you can see the signal strength as obtained from fit in the combined 5 major groups of categories, as well as the combined signal strength, you can see that these results are consistent with each other within the uncertainties. The observed significance that we obtained is 2 sigma, with the expected value of 1.7 sigma, and we set the limits on signal strength at 2.2, and the observed limit on the branching fraction is of 4.7 times 10 to the minus 4. Now moving on to the rare Higgs-2e and lepton flavor violating Higgs-2e mu searches. So here we are testing the BSM models, as the Higgs-2e branching ratio is so small, of an order of 10 to the minus 9, that any hint of a signal would indicate physics beyond the standard model. And also, as I said, the Higgs-2e mu signal would be also an indicate of the physics beyond the standard model, as lepton flavor violation is not allowed in the standard model. And the analysis strategy of these 2 searches is similar to the one in the Higgs-2e mu analysis with partial run-to data. So we select exactly 2 opposite sign leptons. We veto events with BJETs or high ET significance, and then categorize events into GGF and VBF categories. And here we have a cut-based VBF category, where we require a typical topology for this production mode. And all remaining events are divided into 6 GGF categories, which are defined based on the dilepton PT and eta of the leptons. Okay, and in the mu channel, we have additional low PT category where we expect larger fake contribution. And we perform a signal plus background fit to dilepton mass distribution to extract the signal from a falling background. For the signal in both channels, we use sum of crystal ball and Gaussian functions. And the background models differ here. So in the Higgs-2e, we have the same one as used in the Higgs-2 mu analysis with partial run-to data, because we have the same dominating background here. And in the Higgs-2e mu, the background composition is more complex, and therefore we don't have a physics motivated line shape, and instead we use a Bernstein polynomial of degree 2. And in these plots, you can see the combined fit to the mass distribution in the Higgs-2e channel on the left and Higgs-2e mu channel on the right. And we did not observe any signal in either of these channels, and therefore we set the limits at for Higgs-2e at 3.6 times 10 to the minus 4, and Higgs-2e mu 6.2 times 10 to the minus 5th. And these are very close to the expected limits. And these results are are significant improvement with respect to previous results. And now moving on to the Higgs-2e tau and searches. So here again, and because these are lepton flavor violating decays, we test the BSM models. In this analysis, we consider events with electron and tau, or muon and tau lepton in the final states, where tau can decay either leptonically or hadronically. We divide each channel into signal regions, VBF and non-VBF. And we also have defined the control regions in the leptonic tau decay channel for top and Z to tau tau. And we use the BDTs to enhance separation between signal and background in the signal regions. And you can see in these plots, you can see the training variables in different signal regions. So here is the transverse mass and the collinear mass, and you can see they provide a nice separation between the signal and background. And after the BDT, we perform a combined bin likelihood fit to all BDT bins in signal regions and control region yields. And this is done independently in the e-tau and mu-tau channels. And then by doing that, we can constrain the backgrounds and at the same time extract the branching fractions. So here I want to say about the backgrounds. So the main backgrounds here in these searches are events with misidentified objects, and these are estimated using data-driven techniques. We have a large fraction of Z2 tau tau and top events, and for these we have obtained the shape from Monte Carlo, but normalization from the fit. And the other processes like the bosons, the mu, Higgs tau tau or WW, these are constrained to the standard model predictions. And in these plots, you can see the outputs, the BDT score distributions after the fit in the two signal regions. And again, as well in these channels, we did not observe the signal. So we set the limits. So in the Higgs 2 e tau, it's at 0.47%. And in the mu tau channel, it's 0.28%. And the main sources of uncertainties here are the estimation of backgrounds from misidentified objects and of course jet energy scale. Okay, that brings me to the conclusion. Here I presented the result for the Higgs 2 mu search using full run-to data. We observed the signal strength of 1.2 plus or minus 0.6 with the significance of 2 sigma. This is a factor of 2.5 improvement in expected sensitivity with respect to our previous published result. And this comes from much larger data set, but also from the improvements that we included. And these are more categories defined only based on the BDT classifiers, additional categories targeting VH and TTH production, improved background modeling, and the FSR recovery. I also presented here searches for rare Higgs 2 EE and lepton flavor violating decays, for which we observed no signal. So we set the limits on branching ratios. And you can see the limits in this plot here for all the searches that I presented in this talk. That's all for me.
Okay, thank you very much. Questions or comments? Okay, Raffaele, go ahead.
Hello, can you hear me?
Yes.
Okay, so thanks a lot. I have a couple of questions. The first one on slide number 6. So as far as understood, the BDTs trained for glue fusion in the different jet beams are only based on kinematical information or separation between signal and background. How do you account for the evolution of the muon mass resolution with, for example, the PT of the muons or the heat of the muons in classifying the events? And typically, I would be curious to know how the resolution of the muon peak evolves with the BDT score, because I couldn't find the information from the paper itself.
So in each NJet channel, we do have, with the increasing number of jet, we have increasing number of the training variables. So I'm not sure if you mentioned, but we do use the PT of the muon system.
Yeah, but typically, I mean, the PT of the muon system discriminates gluon fusion from Brilliant on the basis of kinematics, but another important information is how large is your peak that you are going to fit, right? And this primarily depends on the position in it of the muon. So if you have a muon pair in the barrel, the resolution would be much better than having, I suppose, one of the two muons or both muons going into another sector of the Atlas muon system. Or in general, the resolution worsens with the pseudo rapidity, right? I was just wondering whether you account for that fact in classifying your events.
I don't think we are using the information about the eta of the leptons. We do use, let me just quickly. So these are all the variables, and oh no, yeah, I don't see the eta, but
okay. So
but
maybe
I think in the BDT categorization we define the categories so that the significance is optimized in each category.
Yeah, sure. So maybe a useful additional information, if I can give a suggestion, would be to add either a table or a plot to the public material showing how the full width half maximum of your peak, for example, evolves in each category to see whether it tends to stay stable or improves with the score of your BDT discriminator.
And this yeah, I can say I don't really know the values in different categories. I know that the best is the width of the best width is 2.6 GV.
Okay. Yeah, maybe we can also chat offline that yeah, afterwards the Zoom room will be still open.
Can I answer to these questions or?
Yeah, this is Fabio. Fabio,
yeah.
Go ahead. Yeah.
Yeah, because I mean, just to add to the answer. So as you see in the BDT, there is the rapidity of the diamond system. So there is a correlation, of course, between the categories and the rapidity, hence the resolution. So we have this table is not public because, of course, we don't make everything public, but at a certain point, we may think to add this to the auxiliary information. And of course, in each category, the signal is parameterized independently. So this is taken into account in the fit. I don't know if this answers your question.
I mean, it's fine. It's fine in the sense that in CMS we have followed a slightly different approach to, particularly for the gluon fusion channel. Then, if I have time, another quick question on slide number 8. So, looking at your combined mass plot for all the categories, just looking at the data minus background, so the background subtracted panel, I see that there is probably as a large peak also around 135 GV. The question is, have you performed something like a p-value scan versus mass?
We checked that. Are you referring to the fact whether we checked the bias induced by the background model?
No, I mean, I see that you have a kind of broad excess, I would say, between 125 and 135 GV, where all the points are above the background prediction. So I was wondering whether you have quantified the observed significance as a function of mass hypothesis, because you are only interpreting for a Higgs of 125 GV, but whether the other points that you have, which is the significance that you have in that specific mass range.
I don't think we calculated the significance for that. I mean, if someone from the group could correct me, but I don't think we did that.
And we didn't do a mass scan because we are not doing a search. So a priori we decided only to look at this mass, but we have checked the quality of the fit both in the 20 categories independently, grouping the categories by production mode and then the global fit. And globally, the quality of the fit is good. Of course, you are pointing out a local fluctuation, but if you take into account the look elsewhere effect, if you don't know that there is something at 132, probably, I mean, the quality of the fits are all good.
Marco, you have also a question or a comment, maybe quickly, and then we should move to our next speaker.
Thank you very much. I just wanted to ask the comparison with the preliminary results, because we see that the mu changed quite a lot from 0.5 to 1.2. So I wanted to ask what are the main reasons for this change?
Well, first of all, the reasons are that we changed quite a lot. I pointed out these differences. This is with respect to the 36 inverse femtobarn, but we changed the category definition. So we moved from 20 GGF-VBF categories into 16 categories. Then we reconsidered slightly the criteria for the background modeling. We added the VH and TTH categories, and we also revisited the FSR recovery selection.
So,
okay, because looking at the data, they don't look too different. So maybe the background model is the main reason of the change, or they all contribute the same way?
I think they all contributed. I don't really know how much each of these changes contributed.
Yeah. So Marco.
Sorry, maybe we should cut a bit this discussion because we are getting.
But I think this I have to answer because it's an important question. Sorry, but yeah, you are right. And this was one of the main worries. So we have done a dedicated study. You find this in the considered material if you look at our Wiki page. So we did a bootstrap study where we consider all the events that are selected either by one or the other analysis and the classification. And okay, this is in the slide. So the compatibility is the level 1.4 sigma, and this is due, of course, to the change in the background modeling, but also in change in categorizations. As you know, this is dominated by the background fluctuations.
Okay, okay, maybe we discuss offline later more, because yes. Thank you very much.
Okay, thank you. Also for nice discussion. So, Bukashin, are you? Can you share your slides?
Can you hear me?
Yeah, we can hear you.
I apologize, I won't be able to share my camera.
Sure.
Okay, let me try with the desktop. Can you see the slides?
No.
Ah, sorry, I haven't clicked it. Yes. Can you see the
Okay,
slides?
very good. Yeah.
Just go full screen. Okay, so hello, everyone. Today we're going to discuss a tale of two studies. Both of them are being connected to the Higgs boson. So basically, after its discovery by Atlas CMS experiments, all the following measurements of its properties have shown a complete agreement with the standard model. But these large uncertainties associated to these measurements can still allow for physics beyond the standard model hiding somewhere. So let's say, why are we interested in the invisible final state? So if we take a look at what the standard model is saying, the branching ratio of something that is invisible, being the neutrino decay, would be extremely small. But this can represent a good way of testing for new physics at the LHC. So can we say something more about the status of these measurements? On the other hand, why would we be interested in something like the dimuon final state? Well, it represents a golden channel for probing the Higgs boson coupling with the second generation fermions, but it is really challenging to do because of the small branching fraction. So is there something interesting that we can say today, and can we maybe update this distribution given on the right? Starting first with the invisible final state. Here in these scenarios, Higgs boson can take a role of a mediator between the standard model and dark matter particles. But in order to be able to detect something in the experiments that we have now, we need to have Higgs boson recoil against something that is visible. And also, in order to quantify this missing part, we're using a variable called large missing transverse energy. Sorry, MET, but it is large in order to quantify it. So starting with the first production mode that is of interest to us is the vector boson fusion production. It brings the largest sensitivity to the invisible final state, and it has specific characteristics by having two jets which are separated with a large eta and a large dijet invariant mass. And in order to approach the irreducible background coming from the standard model V plus jet backgrounds, we use data-driven estimation. Another important example can be a category which is formed around a jet originating from ISR, which can be interpreted as GGH associated with one jet. Finally, we also have VH, which represents a production in association with a vector boson, which can further be separated into the hadronic category or leptonic, depending on the mode of basically decay of the vector boson, but more to come. Speaking in terms of all channels, so the latest combination effort was published in 2019. This has included combination of early run 2, being the 2015 and 2016, with run 1 measurements. And it has set a 95% confidence level upper limit on the branching ratio of Higgs to invisible to be observed of around 0.19. If we take a look at the distribution on the right, we can see the importance of the VBF channel compared to the rest and how the combination effort is presented in terms of the 2016 measurement, where the combination with run 1 is summarized in the distribution given on the right, showcasing the branch ratios for different items and the final combination. The one more interesting thing that is fairly recent is the first run 2 measurement coming from the invisible decays being the ZLL, the leptonic Higgs invisible. It includes the measurement which is performed, again, using the full Ranzi dataset, and when interpreted with a mass of the Higgs being 120 GeV, 25 GeV, it yields a upper limit on the branching ratio of 0.25. And the distributions here are presented as the missing transverse momentum for the for the 0 and 1 jet additional categories. Now, this part concludes the invisible part and leaves us to start discussion about the dimuon final state. So here we are actually interested in events which are collected using a single muon trigger algorithms. And then a common requirement is applied for all channels, where we look for 2 identified and isolated muons within a 110 and 150 GeV dimuon mass range. This range can be further split into a mass signal region, which takes a narrow range of 115 to 135, and the mass sideband region, which takes the rest. What is important to stress here is that we have 3 exclusive channels that are new to the strategy, basically the exclusivity being new. We have now the TTH, VH, and VBF. Starting with the TTH channel, this represents a topology which asks for 2 V-jets where at least one is passing medium ID criteria. And it can further be split into 2 categories, being hadronic or leptonic. The next item on the discussion is the VH channel, where we are essentially looking at leptonic decays of V, and depending on what V is, this can be further split into ZH or WH. Moving on to the VBF, as we saw for the invisible discussion, we can impose a selection of VBF jets, which follows the topology. And finally, we have the GGA channel, which is orthogonality, of course, with, as everyone are, with the rest of the channels, but it represents the largest category and collects all the events which are discarded by other categories. It is mostly dominated by 2 mu plus 0 or 1 jet categories. So starting with a little bit more of the discussion about the channels themselves, but starting with in the reverse order. So we're going to discuss a little bit about GGH, apologize. So in order to separate background being dominated by Drell-Yan processes from signal processes, we're using basically deploying boosted decision tree multivariate discriminator, which is tailored to use muon variables, but is created such way that it has a training which is dimuon mass decorrelated. If we include jet variables in the training, we can recover GGH plus X signal, basically covering all the signals that didn't pass their respective category. And also it is trained separately for each data taking period to incorporate detector effects. So now that we have those events, further division of selected events is basically based on a comparison between signal and background. It represents an iterative strategy done along the range of BDT scores. And basically the criteria we use is to maximize the expected sensitivity from profile likelihoods. So the significance is extracted by fitting dimuon mass with analytical shapes which are inspired for simulation. And if we take a look at this distribution on the right, we can see the GGH BDT output. And these ranges of new categories are represented with dashed lines. So now we know what our categories are. We want to take a look at how our signal and background composition behaves within them. So signal composition is stable across all the categories, and we can model each reduction mode of the signal with a double crystal ball function. And the example of that being given on the right, with the dimuon mass for the combined GGH categories, which are S over S plus V weighted. On the other hand, background's composition follows in a sense that they are also being stable along the categories and being largely dominated by Drell-Yan, with that percentage ranging from over around 90%. We can again model it with discrete profile likelihoods. We can use modified Bright-Wigner, or which are modulated in each category via polynomials. This method also includes negligible bias in the extraction. What is important to stress is that these results are going to be presented for mass of the Higgs boson being 125.38 GeV, which represents the most precise measurement of the Higgs boson mass given with a paper which is referenced here. So on the right, we can see the dimuon mass being represented for all of the GGH categories. Moving on to the next channel, which follows a similar strategy at GGH, is the TTH channel. So this channel can be separated into two categories based on the final state of the W from T decay. We can either have the leptonic, where we have final states including 1 or 2 additional leptons, besides the already having muon pair, where the main backgrounds are going to be TT or TTZ processes, or we can have a fully hadronic final state of the W decay, where the main background is going to be coming from TT. So what do we do here? Again, we ask for the usage of PDTs, and we train them on both categories, exploring both the dimuon and TT-oriented variables, but again, keeping the BDT output uncorrelated with dimuon mass. BDT still learns of the mass resolution due to the reweighting of events before the training, which is the same as with GGH and VH categories, which follow this way of performing the analysis. So further separation is done into additional 2 for the leptonic or 3 for the hadronic subcategories, which are again, in the given example, marked as with dashed lines. So here the example is given on the bottom left distribution with the TTH leptonic BDT output. So in order to approach the fitting procedure, we can use polynomial for hadronic or exponential function for leptonic to fit the background. And basically the summary of this is given on the distribution on the right, which represents the dimuon mass, which is being weighted with S over S plus B for the combined TTH categories.
You have 5 minutes.
Leaving the final category for this approach is the VH channel, where we can have either ZH or VH categories. Similar logic, we train BDTs to explore both the dimuon and the both the dimuon and the ZW topology as well. And again, we can further split into different categories being marked in our examples on the right with dashed lines. So here on the top right, we can have the WH BDT output, where on the bottom right, we see the ZH BDT output distributions. So here again, signal is fitted using a DCB function where background can be modeled via a modified Breit-Wigner functions, but more about those functions, if anyone is interested, can be found in the backup. The distribution of the dimuon mass here represents all of the categories combined. The last channel we're going to discuss here is the VBF channel. So we have discussed the topology already, but the main thing that we want to discuss here is that it differs slightly from the methods used before. So we are going to here, instead of using data-driven methods, which are strongly limited by statistics in the mass sideband, we are going to opt for estimation through the usage of simulated events. So basically we are trading limited data statistics for simulation, which is simulation prediction with associated uncertainty. So signal extraction is done basically separation through the deep usage of deep neural network, which is trained both on signal region and sideband events. So in order to extract the signal, we're deploying a maximum likelihood fit to the DNN output score simultaneously in SR and SB. The constraints in the background normalization improve through the inclusion of this mass sideband in the fit, and the fits are performed simultaneously across regions, but independently of data taking periods. And the post-fit distributions are given on the bottom 2 plots for the basically VBF DNN output bins for the sideband on the left and for the signal region given on the right. So now we come to the discussion of the result. In order to obtain signal strength, we perform a simultaneous fit across all channels, with mu being defined as sigma times the branch ratio observed divided with the standard model prediction. Mu has been measured to be 1.19 for, again, to stress out, for the mass of the Higgs being 125.38 GeV. What is really exciting to say is that we have seen an excess, observed an excess in data with significance of 3.0 sigma. So if we take a look at the distribution on the right, we can see the best fit mu per category compared to the basically combined best fit given by the red line and the, of course, confidence level bands. If we take a look at the distribution on the right, we can see the combined dimuon mass for all categories. But this is just for illustration purposes. It does not represent fit results. Another important thing that we need to mention is that we performed a combination with run-1 measurements, which basically is linked here. And if we want to take a look at each of the categories is, sorry? Did someone try
please go ahead. I'm not sure what was this sound actually. Please
okay,
go ahead.
anyway. Okay, so basically if we want to take a look at how each of the channels production categories is contributing, or how the combination between the run 2 or run 1 plus run 2, we can take a look at the table with the VBF leading the way in terms of sensitivity. If we take a look at the distribution given on the top right, we can see the local p-value for a narrow range of masses of the Higgs, so being between 120 and 130, given for the basically observed distribution given for the combined fit and all the separate categories. What is really interesting is that we can see the updated Higgs coupling parameter distribution versus the particle mass, and basically updated in terms of the muon contribution, which is really interesting to see, especially compared to the initial one. So what am I left to say? I'm only left to say what we presented today and why we're excited again for it. So the combinational effort for the Higgs invisible yields a limit of 0.19 being observed, but the full run 2 result is in preparation, and details about even more like future prospects can be found in a talk by our colleague linked here. What we also presented is the full run 2 measurement by looking at the leptonic Higgs to invisible, and it sets a 95% confidence level upper limit on the branching ratio of Higgs to invisible to be 0.29. On the dimuon side, we're really excited to show the combination of 4 exclusive channels, and to say that we have observed significance of 3.0 sigma being the first evidence for Higgs to mu mu. Combination of performed with run 1 has allowed us to also increase sensitivity by 1. And also we have been able to update the Higgs coupling parameter versus the particle mass, which is a really nice distribution to end the talk on. And basically with having said that, I'm only left to say thank you for your time.
Okay, thank you very much. Fabio, go ahead.
So, well, first of all, congratulations. This is really an extremely important result, and it's a pity that the talk is so short. You should have get more time. But I have 2 questions that are related and are mainly linked to the VBF channel. That is, of course, as also for others, one of the most sensitive ones. So instead of adopting the classical choice of fitting the mass where the shape of the background, it's easy to model, you prefer to fit the DNN shape, and you mentioned that you pay systematics instead of statistics, that I don't fully understand, because at the end, your sensitivity comes always from a very tiny region. So you really need to understand well your backgrounds in this very tiny kinematic region. And in your slide 19, the shape of the side bands and on the signal looks very different. So which kinds of systematics do you include? And the second question that is related is, do you understand why your p-value has this strange dependence on the mass for the VBF? If you go at 125 GeV, it goes down by 0.2 sigma. I don't understand. It should be much smoother typically.
Yes, so the experts can correct me if I say something under the line, but as far as I understand, for the VBF, what they did is they followed through with the data-driven method as well, but being blinded. But they have discovered that this way of approaching increases the sensitivity by 20%.
So including the systematics, but of course it depends which systematics you include, right? You need to control the shape for the Z plus jet at the very, your S over B is still at the percent level, right?
Yes. Okay, so this is as many details as I know. If anyone wants to jump in to clarify more, feel free. But as far as I know, the team has tested both options, and they have came to the conclusion that basically this way brings 20% more sensitivity to this channel.
Yeah, can I comment on this part? Just to help a bit in the reply. So first of all, in the VBF channel, the measurement has a 60% statistical uncertainty. So the systematics are several that we are including. From the theory point of view, the main players are, of course, for the Drellian component, one has to take into account all the theory uncertainty related to part of the shower model, etc., and also for the VBFZ. and because it's another important background at the level of 50% in the last two beams. And of course, experimental one. So mainly related to the jet measurement, jet energy scale, divided in several components, and jet energy resolution. And typically the systematic amounts, the total systematic uncertainty in the VBF channel amounts to 1/3 of the statistical uncertainty that you have, just to give you an idea. Of course, the table in slide that is pointed in that slide combines all the categories together. So it's also taking into account.
I mean, if you tell me how well I can model in this phase space plus jet, I would say I can model with the 50% error. So I mean, of course, I will read.
So I think I'm sorry to interrupt, but there will be more discussion afterwards. Let's give the chance to ask another question by Hong Tao.
Let me also clarify one quick thing about the difference in shape between the sideband region and the signal region. So the DNN in the signal region takes the dimuon mass as input variable. So you see that the shape is sharply falling, because you account for the dimuon mass, and events which are off peak are just migrating to the low score region. While on the left, for the sideband region, we have essentially marginalized the mass out. So you are not including the mass at all. You are using the same network, and you are evaluating it by fixing the mass to the hypothesis used in the training in the signal region. So it's essentially a mass decorrelative DNN, the one that you have on the left. But we are not making a prediction per beam. We are just using sideband and signal region all together to constrain the nuisance that we have on the shape, on the DNN shape. So nuisance are correlated, but the background is not extracted per beam. So you don't need to have the same shape.
Okay, thank you. Hong Tao, maybe you have a quick question as well, quickly, that we are running a bit out of time.
There was one more question that was posed. It was for the p-value of the VBF having a different shape, right?
Yeah, thanks. I mean, I don't want to jeopardize the meeting, but this is a very important result, so I think it's important to discuss.
So just quickly, basically this is, sorry, Raffaele, do you want to go?
Yeah, on that specific point, you need to take into account that in VBF, we are not doing a bump hunt. So essentially, we have a DNN template, which has a certain resolution. And in the last beams, you have very few expected number of events. So statistical jitter, if you have events that are migrating from one side to the other, because you are shifting your mass hypothesis, they can induce fluctuation or jitters in the p-value. So that's why all the curves, apart from the blue one, are smooth, while the blue one has some irregularities, and that is because of the migration between beams.
Okay, thank you. Time to move to our next speaker, but thanks again. So, Chris, are you online?
Yes, I'm here. Can you hear me?
Yeah, we can hear you.
Be able to share my video.
Yeah.
My slides, yeah. Okay, so let me share this so everyone can see these.
Yep.
Okay, great. So yes, I'll be giving a talk on exotic Higgs decays now in ATLAS. One of the big things that we have now is that after the discovery of the Higgs at 125 GeV, we really want to answer a couple of key questions, which is what is the nature of this Higgs boson, and more global, what is the nature of the Higgs sector? And is it completely standard model-like, or are there new interactions that are really waiting to be discovered in this case? The focus of this talk will mainly be on the light states, new light states aspect of this, which are predicted by many theories of beyond standard model physics, especially some theories with naturalness, axions, SUSY, or even dark matter. Additionally, this gained a lot of attention a few years back because it was thought that the gamma ray excess that had been observed could actually be explained by this if this was dark matter basically annihilating through a pseudo-scalar mediator. So from the experimental aspect at the colliders, we have a lot of open room left to discover these new states, let's say. The current model-dependent constraints here coming from standard model Higgs couplings, at least from the ATLAS experiment, are about, the branching ratio of Higgs to BSM has to be less than about 30%. One of the other nice things about the standard model Higgs that we have here is that as there is a really narrow width here at about 4 MeV, small couplings even can lead to very appreciable branching fractions of about 10%. So moving on to the next slide, one of the interesting extensions of the standard model that we'll consider here is really including a second Higgs doublet and also an additional singlet to the standard model. And this 2HDM plus S model really predicts exotic Higgs decays via new either pseudoscalar or scalar states. And we get these nice extra interactions through ZA or AA or SS production, as can be seen with these diagrams over on the right-hand side here. And this basically gives us very new 4-body decays to 4 fermions or even more exotic signatures. So the decays here, though, are to standard model particles, and they're really determined by Yukawa interactions. And so you get many different channels to search through, and the dominant search region actually changes as a function of mass here. So you can see that at lower masses, it's something like light quarks plus maybe muons. In the intermediate masses between, say, 3 and 10 GeV, this is mostly dominated by taus and charms. And then in the high mass region, it's dominated typically by Bs or tau decays. But just to point out, this can change a lot depending on what your 2HDM is. So there's actually quite a lot more experimental freedom here. So I'll really only be discussing some of the newest results from the ATLAS experiment. So starting off, we have the 2B2 mu channel, which really targets inclusive Higgs productions via really the muon trigger to assuming that this A will decay into a dimuon final state. The dominant backgrounds here, because of the 2B jets and 2 muons, are really coming from Zhao-Yan plus jets, which was estimated using a data-driven template in mass sidebands around the Higgs mass. And the TT bar is really Monte Carlo estimated at least for its shape, but this is normalized to a data control region based on higher missing energy because of the presence of neutrinos in the final state for such a background. As the backgrounds are not really resonant in the region 20 to 60 GeV where this search is occurring, we really use the dimuon side of the decay, as you can see sort of diagrammatically in this upper right-hand plot, to basically shift the B-jet momenta to constrain them to something like the mass of the di-B system has to be equivalent to the mass of the dimuon system. And you can see the effect of this is to really sharpen up a lot of the cuts through this kinematic likelihood fit. So you can see that the MBB resolution on the left-hand side before this fit, and after this fit, you really get these nice peaking structures that look very similar to what our dimuon resolution is expected. And so this actually gives us quite a significant improvement in terms of what we can do in order to select on Higgs at 125 events. So the final selections then effectively target this, using this kinematic likelihood fit, then constrain them to the Higgs mass and scan the dimuon range in order to discover if there are any excesses in that spectrum. And so you would expect a narrow peak in the dimuon mass because of the excellent experimental resolution in this region. But unfortunately, we don't see any significant excess above the standard model predictions. And so we set limits on the spectrum basically by scanning the dimuon mass in 2 to 4 GeV wide bins in a range of 20 to 60 GeV. And these actually have provided some of the most stringent limits, at least from the ATLAS side, depending on what 2HDM model we're considering in this case. So then moving on to the next analysis is a Higgs 2AA to 4B. So this search, because of the presence of 4 B jets that are actually very low momentum, we can't effectively trigger on the decay products at that state. So instead we have to look for it in an associated production mode, here being VH. So we use the leptonic decays of the W and the Z to provide the trigger. This also has a nice effect that it reduces the large multi-jet background coming into this search. So the major backgrounds here, because of the high B multiplicity effectively, is coming from TT bar plus jets, often additional heavy flavor jets, although there is a significant contribution from mistags, and Z plus jets processes. These backgrounds are then estimated using some control regions, chosen by varying the jet and B tagging multiplicities in order to have different compositions in those regions. Afterwards, a EDT classifier is basically used to separate out the signal from background using jet kinematics and also some B tagging information. This search in particular requires the presence of resolved single B tagged jets. So in this case, we're looking for 3 to 4 resolved single B tag jets. And you can see that overall, this BDT is separating out quite a lot of the background, as you can see in the right-hand plot, that we're really increasing the significance by quite a lot by using these techniques. But again, no significant excess has been observed. So on slide 8, you can see that we actually then do this similar mass scan, where we scan from 20 to 60 GeV again. Overall, there isn't much sensitivity at the very low mass region. We'll get into that in a few slides. But we set limits on the range 3 picobarns to about 1.3 picobarns as up to the highest mass points. This analysis also had a nice, interesting additional interpretation, which basically was to look for long-lived particles for where these A's are a little bit longer lived. And this actually provides a unique sensitivity in the range where C tau is around 0.1 to 1 millimeter. This sensitivity reduces at longer lifetimes due to the degradation in the B tagging as you basically start to escape the inner pixel layers of the Atlas detector. And so then this is why we see this degradation at longer lifetimes. So then giving a snapshot summary of about a year ago now, where the Atlas results were standing, we see these nice model independent limits on these branching ratios of Higgs to 2x, 2y. And you can see, as I said, there are other analyses that contribute. So for muons at very low mass having quite a good constraint. Mu mu tau tau in this intermediate region is actually able to constrain quite a lot of phase space. And then at the higher end is BB mu mu and 4B dominated. But there is quite actually a lot of unexplored phase space here, quite a lot of white space that we can still explore. But to explore this, we really need new experimental techniques. And so we'll go through a couple of those regions with 2 new analyses from the Atlas experiment. So in the region below about 20 GeV, but above 10 GeV, this A particle is becoming boosted. And so as the dominant decays are typically to BB or tau tau, this results in collimated states, so merged jets, even at this very low mass. And so one of the analyses that's been targeting this is now the same Higgs to 4B final state, except focusing on a much lower mass range. So in this case, 15 to 30 GeV in only ZH production. The dileptonic decays of the Z are used to trigger this, and this is really needed to cut down on a lot of the multi-jet background that is coming in. They also have a dedicated MBA tagger using B tagging, jet substructure, and kinematic information, because as I said, these jets are merging. So what they actually have to do is to take the basically, you have 2 B jets in what would be considered as R equals 0.8 jet, and they run exclusive KT on this in order to separate out the 2 subjets. And basically, by doing this, they can gain some information on the subjets from the B tagging scores and use this to distinguish this between the background where we have single B decays versus this merged 2 B decay case. The dominant backgrounds here, again, showing now the composition over here, comes from the Z plus jets and TT bar, and these are estimating control regions, again, taken by varying the tagging purity and also the dilepton mass constraint either being on Z or off Z in order to get more TT bar events. Yeah, thank you. And so then unfortunately, so we see the control regions and the signal regions after all the analysis selections are made here, and we see no significant excesses. But this is the first LHC result in this very low mass 4B state to use actually some merged B jet tagging. We're only really beginning to probe the phase space below 100% branching ratio of Higgs to 4B. So you can actually see this only is sensitive to new phase space, let's say below right around 20 GeV. But there is significant gain with respect to the previous analysis, almost a factor of 2 or more, as we can see where this old analysis was losing sensitivity. But there is still a lot of places to go. And so this is a very nice first result that we've been able to accomplish. And so then going back to the slide and looking now at this other mass region. So in this region between about 2.5 to 2 mass tau, the A particle is becoming very boosted. And these dominant decays are either to light gluon jets, or in some cases, the branching ratio can be appreciable in muons, but we have Corconia decaying in this region as well to the same states. So you can, again, look for these in merged jet final states. And so the one of the new analyses, Higgs to ZA. So this is where the Z will go to leptons and this A is going to hadrons, is basically trying to look for this ZA decay of the Higgs. And this targets the inclusive Higgs production and the triggers provided by the leptonic Z decays. So the search really is looking for these A hadrons in a very low mass state between about 0.5 GeV to 4 GeV. And there are additional sensitivities to perhaps enhance decays of the charmonium states. So in this case, the A to C and J psi elements. The decay signature, however, is very, very interesting in that it's a single anti-KT radius equals 0.4 jets. So you have a massive background coming from Z plus associated jets or Drarian plus associated jets. And so in order to really separate this out from the background state, you have to use a neural network to discriminate this merged jet signal from a single jet background. And this basically relies a lot on the track-based jet substructure information, which you can see a bit what this mass estimation is doing in this neural network in the upper right-hand plot. And you can see that it actually can separate out very light states fairly well, but as we get heavier, this is actually becoming a bit more background-like. And additionally, the same thing can be seen in the lower right-hand plot. The Drarian plus jets background is estimated using ABCD method in the MLLJ discriminant. So we're basically using a single jet to determine the mass of this total ZA system for LLJ, and the neural net discriminant sidebands in order to enhance the background. So after using this neural network classifier to select the most signal-like regions, they cut on the LLJ mass to be consistent with the Higgs mass of between 120 and 135. And so you can see that in the right-hand plot that there is no significant deviation from the standard model hypothesis here. And so limits are produced on these exotic decays. So the upper limit on the branching ratio of Higgs to ZA, assuming this A boson is decaying exclusively to gluon or SS bar states. And here you can see both of them. And these are providing quite actually nice constraint below about 2.5 GeV, but then they quickly lose significance or lose some constraining power. And so the limits also on the Z to charmonium states, because they're higher, are greater than 100%. So they're about 110 picobarns to 100 picobarns. But it is quite a nice first analysis as well for this very low state that is very, very complicated physically. So that brings me to my summary. So several new searches have been performed by the ATLAS experiment with targeting the production of new light resonances in the case of the 125 GeV Higgs boson. No significant deviations, unfortunately, have been found from the standard model, but the decays to these new final states are starting to provide sensitive probes of new physics in the Higgs sector. To fully exploit this vast open phase space, we now need new experimental techniques to cope with challenges such as jet merging and low PT final state objects in these decays, and new results from ATLAS have really shown the first effort on some of these more challenging final states. And we expect many new exciting results and possibilities for the full run 2 analyses, and also looking forward to run 3. So that's it. Thank you.
Thank you very much. Questions or comments? Yeah, I don't see any question. Yeah, maybe a general question I had. I mean, I'm a theorist, but I'm curious. So you show these nice summary plots of all the searches, and I wonder if there are other plans for looking for merged states, also for the other searches that are shown here.
Yeah, so there can be quite a lot of interesting things done in the mass region. So I know, and maybe it's being discussed in the next talk from our CMS colleagues on mu mu tau tau, for example. And so these searches are particularly interesting as well for those cases. I think that it is very interesting for basically anything below 20 GeV. And even above 20 GeV, we have to be a little careful depending on our production mode because of the Higgs PT. Yeah.
Right. Okay. Thank you. Yeah, I don't see any other raised hands. So maybe, yeah, thanks again.
Thank you.
And let's move to our next speaker, Feng Guan Dong.
Hi, Stephanie.
Hey.
Can you see me?
Yeah, I can see you.
Okay. First, I thank for all the organizations and thank the Chris for bringing my topic up. Yeah. My start. Okay, just a second. Let me share my screen. Okay. Yeah, it's a little bit tricky here. Do you see it?
Yep, can see it.
I'm going to full screen now. All right. So good afternoon or good morning, everyone. Yeah. Anyway, so my name is Feng. So today I will present the latest searches for exotic Higgs bosons decays. Yeah, on behalf of the CMS experiment collaboration. All right, so first I have a general review about the motivation. So since we discovered Higgs boson about 8 years ago, so we have been working on measurements currently on the Higgs coupling to standard model particles. So far, yeah, most of things are consistent with the predictions. But by the current physics limits, so the beyond the standard model decays were not completely excluded. So any deviations from the prediction could give a hint of beyond standard model. So basically in the left bottom plot, you can have a look at the upper limits of the branching ratio of the Higgs decay to undetectable particle or invisible particle, yeah, which were measured by the latest CMS experiment round 2 results. So basically, if we assume the branching ratio of the Higgs decay to undetectable particle to 0, so then we got about 47% on the limits at a 95% confidence level. Yeah. So basically, this is also a new starting line, yeah, for the full round 2 analysis measurement. And then the the right bottom plot. So basically, you see the CMS delivered integrated luminosity during the last decades. Yeah, so we hopefully to achieve more sensitivity and large statistics with the full round 2 data plus round data combination if possible. All right, so here I just list the CMS searches for the exotic Higgs decay. So basically, there was many studies have been done, with full round 2 or partial round 2 data. So basically, a few of them have been covered by my colleagues' talk. So I just put them here. And today I will just focus on the 3 analyses, basically marked with the green color. So first analysis is the Higgs decay to Z boson plus meson, which is a 0, 0 or the phi. So in the middle, you can see the Feynman diagrams. Yeah, basically the Higgs coupling to a Z boson on shell, and another off shell Z gamma boson. Yeah, decay to opposite charged quarks, and then gives rise to the meson in the final states. So they give important information about the couplings between the light flavor fermions and the Higgs boson. So this process have a very small branching fraction. Yeah, I list the number here, you can see them. So in order to conduct the analysis, we collect the events and require 2 opposite charged leptons from the Z decay, and then the other 2 reconstructed isolated tracks, which are also opposite charge. All right, so in order to perform the analysis, so we have to do the maximum, I should say that the final states of the rho decay is the pi plus, pi minus, and the phi final decay particle is a Chian, plus or negative. And so we use a bin template to model the signal and also assume the branching, larger branching ratio in order to achieve sensitivity. Yeah, and the background was modeled by Chebyshev polynomials, and then we perform maximum likelihood fit on top of that. So basically, you can see the two plots on the top. So left is the Higgs to z plus 0, and then right is the Higgs to z plus 5. Yeah. So you can see in general the data-driven approach behave very well, and the fit quality is also good. And we didn't see a significant excess above the background estimation. So based on that, we set the first experimental limits on these two decay channels in 95% CLS. So the Z plus 0 channel is about 1.04 to 1.31%. And then the Z5 channel is about 0.3 to 0.4%. Yeah. So, all right. Then next topic is about 2 HDM plus S scheme. So it's the scalar fields in the Stanmore Lagrangian, with the two doublets things. So they basically have 4 different type of coupling to the fermions. So you can see the bottom table summary here. So just the short reminder that among them, the type 2 is the minimum supersymmetric model, and type 3 is the enhanced couplings to leptons at the large time beta especially. And with the scalar singlet for the extinction, we have an MSM for that type 2, and then we got natural light scalars with this scheme as well. So basically we got 5 physical states predicted with a spontaneous symmetric breaking scheme. Yeah, so you can see the list there in the middle. All right, so based on the theoretical introduction, this brings to our latest accepted analysis by ICHEP, which is Higgs to A to 2 mu 2 taus. So basically the 2 mu give us clean signature on the analysis process, and the 2 taus have large branching ratio relatively, yeah. And we conduct analysis with compatibility with the standard model Higgs boson or a heavier Higgs boson, decay to pseudoscalars. And the pseudoscalars mass range from 3.6 to 21 GeV. Yeah, so that means in most cases, we have a boosted topology for the dimuon pair and the ditau pair. So in order to achieve, let's say, good significance and sensitivity with a target probe approach, so we choose the semi-leptonic decay channels for the ditau, which is the tau mu plus tau head. Yeah. All right, so I got to leave this screen shared by this thing. Okay, let me move this. So, okay, so basically, as I mentioned, in order to cope the boosted topology for the ditau pair, so we invent sort of a new scenario for the tau reconstruction. Because the standard way to reconstruct the hadronic tau is to just use jet seeds, which include all the particle flow candidates in the jet cones. But for other case, so we clean the muons from jet cones in order to let's say, to cope with the boosted topology. And of course, the reconstructed tau head could be like 1 prong or 3 prongs, yeah, plus a different number of pi zeros if possible. And in the bottom, so we do a comparison between the standard way to reconstruct tau head and our customized way to reconstruct the tau, yeah, well, after the muon cleaned. So you can see the left plot here, the solid curve corresponding to the second scenario and the dashed line corresponding to the first scenario. So you can see with the second scenario, it's the efficiency is significantly increased. Yeah, so that's why we adopt that. And there's a little bit efficiency decreasing at the low mass area. This is because the muon become more collinear with the tau head, which is more difficult to be separate between them. All right, I have trouble to, okay. All right, so based on that, so we can perform our background estimation. So again, our background is dominated by the Drell-Yan jets. So in order to accurately estimate that, we use a data-driven approach. So we basically perform the parameterized signal and background distribution, and then conduct a 2-dimensional unbinned maximum likelihood fit. Yeah, and then between different generated A masses, we use a polynomial function to interpolate. So in order to achieve higher significance and sensitivity, we choose two variables to perform the 2D fit. So one is the diameter mass, and the other is the visible mass of the full body. So here you can basically see the top two plots. Left side is the diameter mass spectrum, in the spatial mass range, in the spatial range. Yeah, so here in this range, we suffer the dominant epsilon peaks. So basically, they are modeled by a Gaussian profile in the fit procedure. And then the background trend is using the exponential trend. So and then you can see the red color peak, which is our signal at the 9 GeV pseudoscalar mass. Yeah. And with the branching ratio assumption, 5 times 10⁻⁴. And the right side, so this to fit the visible mass of the full body, so we use the convolution of the two pairs of error function and exponential. Yeah. So in general, they perform very well. Of course, we don't have enough statistics with the 2016 only data. So basically, we hope to have more statistics for this study with the full round data later. All right. So based on the, sorry?
You have 5 minutes.
Thank you. Yeah. So based on that, we can perform the limits sets. So here we have the model independent limits on the MH125 for the light precise scalars ranging from 3.6 to 21. And then the right side, we have the first model independent limits for the heavier Higgs mass, 300 GeV. So basically there were mainly 3 peaks in the middle due to influence of the epsilon resonance and also the large uncertainty from the background model over there. All right, so then the third topic is the Higgs decay to dark photon. So basically we have 2 channels, Higgs to Z plus dark photon or Higgs decay to 2 dark photons. So this model is basically a median particle with a dark gauge symmetry and broken by the dark Higgs mechanism. And the 2 channels have different interaction types, which is kinematical mixed coupling through hypercharge or Higgs mixing coupling, through the Higgs bottle. So, so we basically to start the background using data-driven approach, which is the Z plus jets again. So the left side is the Higgs to Z plus dark photon model, and the right side is Higgs to the double dark photon particles. So in both cases, you can see that the statistics are not very high and no significant excess above the standard model predicted background. So we got background, let's say especially ZZ, and for the Higgs to Z plus X, and we got ZZ and TTZZ and WWZ for the Higgs to double photons, dark photons. So basically we conduct 4 different decay channels. So here I just laid 2 of them. So most of them were covered in backup. All right, so based on that, we can extract the limits on the branching ratio as a function of the dark photons mass, from about 4 to 35. So basically, you can see the left side is Higgs to Z plus the dark photon, and right side is Higgs to the double dark photons model. So we basically set the exclusion limits, with the expected and observed value on top of that, with a theoretical prediction there. So the epsilon maximum states range is excluded because the switch from the experimental driven uncertainty to the theoretical one, And the largest uncertainty, of course, is dominant from is the background estimation. All right, so this brings to my conclusion. So far we have already made many progresses in the Higgs exotic decay. Of course, I just show 3 of them, as the latest results. So in general, we don't have significant excess above the standard model predictions. So but we achieved the increased let's say, stringent constraint, yeah, with the round 2 data than the round 1 legend. So today I just present first the limits on the Higgs 2Z plus meson channel, and the upper limits on the light excitoscalars for MH125 and 300, and also the dark photon models in the search. So we would hope more interesting results coming soon with the full round 2 data, yeah, which is also true. And in the long term, so we have to, let's say, hope to realize higher sensitivity and also, yeah, high significance with large data sets above round 3. Thank you for your attention.
Thank you very much. Questions, comments? Tanya?
Hi, can you hear me?
Yes.
Yeah, I can hear you.
A very quick question on slide 10.
Slide 10.
Yeah, exactly. Just very, you were already there, exactly.
Mm-hmm.
So this on the right-hand side, this sigma standard model normalization factor, that's the one for the 125, or is it a standard model prediction for 300 GeV scalar?
You mean which value?
On the right-hand side, sorry,
right hand.
Action, the sigma SM, is it the one, the production cross-section for the 125 GeV or for 300 GeV?
So I think it was for 300 GeV.
For 300,
yeah,
okay. So it's a...
Yeah, yeah.
All right. Thanks.
That's right, for a standard model like Higgs at 300.
Exactly, yeah, yeah. This was for me a little bit unclear, and okay, thank you.
Okay, any other questions or comments for our speaker? Okay, yeah, I don't see any question also in the chat. So yeah, thanks again for the nice talk. And
thank you very much.
Let's pass to our next speaker. Ben, are you?
Yes. Let me share my screen.
Yeah, that would be great. Okay, perfect.
Okay.
Go ahead.
All right.
Thank you.
So I am going to talk about searches for invisible Higgs boson decays at the ATLAS experiment. So I'll give a quick introduction. Some of the ground here was already covered in Fukushin's talk earlier, but we're looking for evidence of Higgs production, plus a large missing transverse momentum from the decay of the Higgs to some invisible particles that we do not observe in the detector. So this can happen in the standard model if the Higgs decays to an all neutrino final state, but it's a very rare process. It has to happen through H to ZZ star to neutrinos. And the branching ratio for this, this channel is something like 1 in 1,000. So it's very unlikely, but it can be significantly enhanced in many beyond the standard model scenarios. One in particular I'd like to highlight is the prospect that the Higgs might couple directly to dark matter. This is the Higgs portal class of models, where the Higgs provides a portal or a bridge between the standard model sector and the dark matter sector. So this analysis can be done in any of the Higgs production channels. The most sensitive one is vector boson fusion. Due to the distinct event topology of VBF, makes it easier to reject background than gluon-gluon fusion, even though GGF is the more common Higgs production mechanism. So on slide 3, let me talk about the sort of previous results in ATLAS, and then before going on to present some new results. So this is a plot from our version of the Higgs, our Higgs combination, Higgs to invisible combination, with partial run 2 data, so 36 inverse femtobarns taken through 2016, and it contains 3 analyses. So from left to right on the plot, there are 2 Higgs-Stralong channels, B hadronic and Z leptonic, and then there is a VBF analysis. And I've printed out the observed and expected limits for the 3 analyses and then for the full combination. And VBF is driving the sensitivity of the combination. So that's these are results with a partial run 2 data set. Today I'm going to present 2 new results with the full run 2 data set. One is an update to VBF that was actually released back in April as a physics briefing in lieu of Moriond. The other is a new update to the monojet analysis that has just been put out for ICHEP, that contains a gluon-gluon fusion Higgs to invisible interpretation that was not done before by ATLAS in run 2, which is why it's not present on this plot. All right, so slide 4. Let me talk about VBF Higgs to invisible. So what is the VBF event topology? Well, you can see an example event in this event display. The event topology is two jets, a jet pair with a large rapidity gap between them, and jets in opposite hemispheres of the detector, a large dijet invariant mass, and then a large missing transverse momentum from the decay of the Higgs. So what are the backgrounds? The main backgrounds are a Z boson plus jets, where the Z decays invisibly to neutrinos, and a W boson plus jets, where the charged lepton is lost. It's not reconstructed in the detector, and so it too appears to decay invisibly. So, and the careful estimation and precise measurement of these backgrounds is the main challenge of the analysis. So I just want to quickly highlight a couple of changes from the previous 36 inverse femtobarn result before talking about the background estimation in more detail. We re-optimized the 36 inverse femtobarn result. That re-optimization led to a large increase in Higgs signal acceptance by about 50%. Part of that re-optimization involved changing the way we do our fit. Instead of simply doing a one-dimensional binning, where MJJ is the variable that we bin in, we now have a multi-dimensional binning that looks at MJJ, delta phi JJ, and the number of jets. And then the previous analysis of the 36 inverse femtobarn result was limited by Monte Carlo statistics in the background estimation. And so work has been done to improve the V plus jets modeling and reduce the Monte Carlo stat uncertainties. So before moving on, I just want to say that Amanda Steinhubel presented a poster on this analysis, I think this morning. So I've linked to that contribution. If you're interested in more details, I encourage you to take a look. Let me go to slide 5 now and talk about V plus jets background modeling. So we generate Monte Carlo, and for the V plus jets processes, we generated it next to leading order in QCD. But then we use a partially data-driven technique where we define 1 and 2 lepton control regions. And you can see plots here of the 2 lepton, the Z control region, and the 1 lepton W control region. And we look at the ratio of data to Monte Carlo, and then take that ratio and we use it to correct, to rescale the Monte Carlo in the signal region in order to improve the accuracy of the estimation. Now, this is done separately for each bin. So each bin, the background estimation can fluctuate independently, and it's also done separately for W and Z processes. So there's the Z to LL is used to constrain Z to nu, and the W is only used to constrain the W loss lepton background. Now, I said we were Monte Carlo statistics limited. The reason for that has been that one of the reasons the high MJJ cut is useful is because it constrains the W strong and Z strong backgrounds, which are much less likely to occur at high MJJ. But by simulating them next to leading order, it becomes very expensive to produce enough Monte Carlo in this phase space at that accuracy. And so it is difficult to get enough events to really precisely to do this measurement. So for this version of the analysis, we collaborated with the authors of the Sherpa generator to artificially boost the statistics generated at high MJJ in order to try and bring down those Monte Carlo stat uncertainties. All right, on slide 6, I want to now talk about another background for this analysis, which is the multi-jet background. This is a small background, but it requires a sophisticated data-driven technique to estimate. So I thought it was good to go through it. So the diagram here sort of shows what we are doing, and I'll talk through it. But this is a background of QCD-like events that have a fake missing transverse momentum due to a jet mismeasurement. So what we do to model it is we take data, we extract from the data a population of events that are QCD-like and have no missing transverse momentum, and then we smear the jet response. So we essentially we simulate the jet mismeasurement in order to get a population of QCD-like events that are known to have fake missing transverse momentum. Now, this is done separately for events that have pileup jets and events that don't have pileup jets. If you look at the plot, which shows a very loose multi-jet control region where this estimate is normalized by a fit to data, you can see there are 2 multi-jet bands. One has pileup jets, and then the blue one does not have pileup jets included. So from this fit to delta phi JJ, we get a multi-jet estimate. We take that multi-jet estimate, and then we check the closure in a low MET and low MJJ version of the signal region. So while it's a small background, it's an involved procedure that is important to get right. All right, on slide 7, let me now just show you the results. So this is a post-fit plot showing all of the regions and all of the bins in all of the regions after the fit, and the fit is where the transfer factors are applied. So from left to right on the plot, on the far left, there is this fake electron control region, which I did not talk about, but this is a region to estimate another multi-jet background, but a multi-jet background where we improperly identify a jet as an electron. And you can see the purple in the W to E nu control region is a small background, but it needs to be understood so we can be confident that we can extrapolate from that control region. Then there's the W to mu nu control region, which is handled separately precisely because of this issue, and the Z to LL control region. And so then the transfer factors are extracted from those. And finally, we have the signal region on the right. And in the signal region, you can see that there is no significant disagreement with background after the fit in any of the bins. Slide 8, we can look at this, not just as bins, but look at the MJJ and delta phi JJ distributions, which are the main variables that we bin in. And you can see again here that there is good consistency with the background only hypothesis. I'll just say that the red line on these plots, the Higgs signal, has been scaled to the expected limit on the Higgs to invisible branching ratio, which we're going to set as 0.13. And that signal contains all possible Higgs to invisible signals, so not just VBF. And while it is 87% VBF, there's actually about 12% gluon-gluon fusion there as well, and then a tiny amount of VH events. Okay, so slide 9. So there's no excess. We can set a limit. So the expected limit is 0.13. The observed limit, at 95% confidence, is also 0.13. So there's definitely no excess here. Very good agreement between data and background. This limit of 0.13 is a significant improvement from the 36 inverse femtobarn result, where the limit was 0.37. So this is about a factor of 3 improvement in the observed limit just in this channel alone. And just to say that the largest sources of uncertainty, the largest impact on that limit is now driven by data statistics, although the background estimation systematics of V plus jets and Monte Carlo statistics and then multi-jet are then the next most important uncertainties. So just to put this result, this 0.13 into context, it can be, if the Higgs portal dark matter that I mentioned, we can interpret this as a limit on the spin-independent WIMP nucleon cross-section in Higgs portal models for a couple different Higgs portal models. This lets us compare directly with the direct detection experiments, and that's what's shown in this plot here. The blue and the red lines are 2 different possible Higgs portal dark matter scenarios with our result being used to set the limit. And you can see that we have very nice complementarity with the direct detection experiments.
You have 5 minutes.
Okay, perfect. Yeah, so on slide 10, I'll just use my remaining time to talk about the monojet analysis. So this is a search for at least 1 jet plus large missing transverse momentum. The Feynman diagram shows sort of an example signal process with initial state radiation plus some new propagator that decays invisibly. So this is similar to VBF, similar analysis to VBF Higgs to invisible in a number of ways. The main backgrounds are the Z plus jets with the Z going to neutrinos, the W plus jets with lost lepton. And of course, there are many possible dark matter interpretations here. So I'm not going to talk about any of them except for Higgs to invisible. But Ben Carlson gave a talk yesterday in the dark matter session that sort of highlighted the Atlas dark matter search efforts, and it has some more details there. So I encourage you to check that out for more information. One thing I'd like to say is that I sort of said earlier that this was not, the Higgs to invisible interpretation was not done in the previous round of the monojet analysis. The reason it's possible to do now is that the MET threshold for this version has been lowered from 250 GeV to 200 GeV, and that increased sensitivity at low MET has made it possible to set a limit on the invisible branching ratio. Okay. So I want to talk now about the background estimation for the monojet analysis. And I'll just say that work was done to improve that here as well. And there was a collaboration with theorists in order to try and improve the accuracy of the background estimation. I'll talk about that on slide 11. So the same sort of transfer factor approach, is data-driven transfer factor approach, is used for monojet. A couple of differences is that thanks to this collaboration with theorists, Jonas Lindert et al., I've cited their paper here, the Monte Carlo they use has actually been reweighted to an even higher accuracy. So it's been analytically reweighted as a function of boson PT up to NNLO in QCD, NLO in electroweak, and NLL in up to 2 Sudakov loops. Also, as a result of this collaboration, the process correlation model was built between the Z and W processes, which made it possible to use the W to help constrain the Z. So unlike VBF, where there are 2 transfer factors for V plus jets, in monojet, there is only a single transfer factor for both Z and W. Now, one other difference here is that there are also transfer factors for top backgrounds. So there's one for TT bar and one for single top from a dedicated top control region. And I've included post-fit plots here from monojet showing the W control region and then the top control region. And now if you look at these plots, they're plots of this variable PT recoil, just to say that that is simply the vector sum of the missing transverse momentum and the leptons. So sort of adding the visible recoil into the MET in order to, for the control regions in analogy to MET. Okay, so on slide 12, let me just now show you the results. So a shape fit is done to PT recoil across all regions, and there is no significant excess observed. I'd like to highlight that the total uncertainty is really quite low. It's like 1 to 4% across all bins. And this low uncertainty is more than a factor of 2 improvement from the 36 inverse femtobarn monojet analysis. What drives that uncertainty? Well, the main systematics are electron and muon identification and reconstruction. So the analysis is systematically limited. The background estimation systematics do matter as well, especially at the low PT recoil end where multijet is relevant, and at the high PT recoil end, V plus jets estimation. What about the Higgs to invisible interpretation? Well, we can set a 95% limit on the Higgs to invisible branching ratio for monojet. The observed limit is 0.63. The expected is 0.57. Now, I said this was in a gluon-gluon fusion channel, and it is primarily gluon-gluon fusion signal, but there's actually quite a bit of sensitivity to VBF and VH as well. So 34% of the Higgs signal yield is VBF and 12% VH. All right, yeah, so to conclude, I've presented 2 full run-to Atlas searches for invisible Higgs decays. The VBF limit on the invisible branching ratio of 0.13 is a significant improvement from the previous Atlas results, both in the VBF channel alone and in the full combination. And then we have new results from the monojet channel, and both of these will be included in a forthcoming Higgs to invisible combination, along with updates to the other channels. Thank you for your attention.
Okay, thank you very much. Questions or comments? People are getting tired. So maybe, yeah, I have a comment that is rather obvious, but you know, on slide 9, when yeah, here. So in this plot that you show the interpretation in terms of this spin-independent cross-section and the comparison with direct detection. So the comment that I had is that this interpretation can be done also for dark matter masses below 1 GeV, correct?
Yeah, I think so. I think it's just cut off here in the plot.
Right. Yeah. So I'm mentioning this for a reason that I mean, obviously there are experiments that are also looking for dark matter below the 1 GeV mass in direct detection, and you know, having the comparison with these bounds could be interesting. So at a certain point, one could look also for this interpretation below the 1 GeV. But
sure.
Yeah,
we could consider trying to include some of those experiments as well in a more detailed,
yeah,
or an expanded version of this comparison.
Okay. Yeah, let's see. Yeah, I don't see any raised hand. So maybe, yeah, thanks again for the nice talk. And let's move on. Let's move to our next speaker. Nick.
Hi. Can you hear me?
Yeah, we can hear you. If you could share your screen with the slides. Okay, very good, perfect. Okay.
Okay, let me briefly introduce myself. Hi, my name is Nick Smith. I'm a postdoc at Fermilab, and I will be talking to you about Higgs boson measurements in hadronic final states at CMS. And I'll stop my video now just to conserve bandwidth. Okay. So, hadronic Higgs decays. Why do we search for these? Well, of course, the main motivation is the large branching fraction. Over half of the Higgs, well known to decay to BB. But if you think about it, actually, the vast majority of Higgs decays are actually hadronic. It's not until you get to the 5% level that you start talking about leptonic and more classic golden signatures. So in fact, the majority of the Higgs we have are hadronic Higgs, so it's worth looking for them. And in many of the cases, they are a direct probe of fermionic couplings, whether that's BB or CC or tau-tau. You have a direct access to that Yukawa coupling. So that makes them attractive as well. But of course, the main challenges are, well, hadronic decays involve QCD, so you have very poor kinematic resolution in these jet final states. You also have to deal with what seems to be an insurmountable amount of background, both trigger level and offline. And to add to the complexity, the simulation that you do have of these QCD processes is often untrustworthy, whether that's due to heavy quark phenomenology or just being able to produce enough simulation statistics to accurately represent the data you've collected. Nevertheless, CMS has overcome these challenges and published results in H to BB channels, H to CC channels, and also some other ones that I won't talk about here. If you're interested in Higgs to tau-tau, there'll be a talk tomorrow. So what I'm going to do is I'm just going to dive into the current state of the art from CMS and H to BB and H to CC, and then I'll take a detailed look at one of the most recent results in boosted H to BB. Okay, so the most recent CMS H to BB results are in 3 of the 4 production modes have been published using partial run 2 data. So there's the VHBB, which actually saw a 5 sigma observation for the first time in this particular channel. The TTHBB is a quite impressive analysis that considers basically the entire mess of combinatorics that comes from a TTH production in a almost entirely jet final state. They do trigger on a lepton to save themselves though. And then there's this boosted gluon fusion H to BB result, which at the time of this combination that I mentioned here was the only result, and it's been superseded by the result that I'll talk about in a few minutes. So all of these have been sort of combined into this sort of Higgs combination super likelihood, and you'll hear more details on that combination tomorrow from Adinda DeWitt. And it's very hard to look at this many decay rates, this many production modes all at once. So if there's one thing I can ask you to take away from this combination is that the decay rate modifier constraint on Higgs to BB is actually the same order as the so-called golden modes like gamma, gamma, and ZZ. So in fact, we're actually extracting very useful information from Higgs to BB, a very messy hadronic state, as well as we are from, say, ZZ to 4L, which is a very clean final state. So I think it's really impressive that a very hadronic mode can still give us good constraints on the Higgs properties. To make things even harder, we start looking at HCC, so 20 times less production than BB, yet using a combination of strategies, we can attempt to set limits on it. So in this direct probe of VHCC production, we tag a vector boson on one side of the event using all the lepton multiplicity categories. And basically the idea here is that whether it's through MET or lepton triggers, you have a chance to actually capture this event in the first place. And once you have these events, then you approach it from two strategies. If the transverse momentum in the event isn't too much, then you take a resolve strategy where you look for two charm-tagged narrow radius jets. So that for us, that's AK4 jets. And then you use the kinematics of the tag bosons in these charm-tagged jets to further reduce background. And for the boosted strategy, you now have a collimated Higgs jet. And so you approach it from this deep neural network double charm tagger called the Deep AK8. And the idea is that you can, there's a certain advantage of considering both prongs of this boosted jet at once to better reduce the backgrounds. The downside of this is you sort of lose the two independent tag jets now. You only have one double charm tag jet. So it's a bigger challenge to constrain the backgrounds and properly predict the tagger efficiencies. Luckily in this VH channel, there's you can use the kinematics of the tag boson on the other side to sort of construct control regions that allow you to evaluate this deep tagger efficiency and put proper constraints on the data efficiency of this deep neural network. You combine these two together, you get an observed upper limit on VHCC production of about 70 times the standard model. So we're not there yet, but this is only 1 year of run 2, and we may see an update in the future. Okay, so now I'm going to dive into, I guess, the latest result in this BB channel, which is this full run 2 analysis measuring high transverse momentum at Higgs to BB production. The overall strategy here is to pre-select a boosted large radius jet with two-prong substructure. So by large radius, I mean anti-KT, R equals 0.8. And we use this deep double B tagger, which is, again, a deep neural network, to select BB enriched events and constrain the giant QCD background with a special technique that I'll talk about in a few slides, and then search for a peak in the jet mass distribution. So why do we want to do this? Well, after the previous result, there was an effort by the theory community to sort of put together as precise a prediction as they could for boosted Higgs production. So we have gluon fusion Higgs production, Higgs plus 1 jet at something like quasi double NLO, in the sense that it's H plus 1 jet at double NLO in sort of the heavy top effective field theory, but then corrected to consider resolve top effects at up to 2 loops, which is actually really impressive, as I understand it, to calculate the 2 loop amplitudes. Then the other production modes are also tabulated at their best respective order. For our analysis, they are subdominant to gluon fusion, as you can see in the right-hand plot, but they are not insignificant, and some of them do rise with transverse momentum. And it almost goes without saying that any beyond the standard model coupling can easily change its spectrum, and it can also easily change it without spoiling the inclusive cross-section, which has been measured quite well by the Atlas and CMS collaborations by now. You can imagine, some other particle running in these loops quite easily. Okay, so how do we get these events? Well, we trigger on a high transverse momentum large radius jet, or just the total transverse momentum in the event. We select a leading transverse momentum jet within some kinematic phase space. And to assign a mass to this jet, we use the so-called soft drop mass algorithm, which removes soft and wide angle QCD radiation to improve the resolution. So you're really getting that resonance mass if it is a resonance. And then you require a 2-prong substructure with this N2 energy correlation variable. The idea is it's relatively independent of mass and PT, so it sort of gives you a flat response over the phase space that we're probing. We do take a hit from that selection that we lose about 40% of our signal, but it's worth it because it also removes a significant portion of QCD background. There are various other, targeted rejections that just remove anything that has leptons in it. Okay, so of course the main discriminant in analysis is this deep double B tagger. So the working point that we use is this 60% efficiency on the gluon fusion signal at 1% QCD efficiency. And so it includes all the inputs of the previous analysis tagger, which was a simpler boosted decision tree, but also starts to include low-level variables from tracks and secondary vertices. And so going to a deep network was really necessary to reliably exploit such low-level variables. At the end of the day, okay, thank you. At the end of the day, you end up with about a 1.3x efficiency gain versus the previous analysis at the same QCD working point. Okay, so now that we've tagged these jets, how do we estimate the residual QCD background? So the idea is we use what we call a differential ABCD method, or alphabet method. We have this region of huge statistics from all the events that failed this deep double B tagger. And we, as I said before, we have a lot of difficulty using simulation to predict this simply because, I mean, there's just so many events that failed this. It's a very inclusive analysis. So what we do is we actually let the data tell us the shape of this QCD background in this fail region, and then fix the pass region by some transfer factor. Now, if you imagine in a classic ABCD, this would be a flat transfer factor, and essentially the side bands of the mass spectrum is predicting the yield under the peak. You can imagine, region A is one PT bin in the fail, region B is another PT bin in the fail, region C is one PT bin to the side of the peak in the pass, and therefore region D is predicted by those other three. Now here we actually allow some correlation between the respective PT bins. Basically, this is attempting to capture any residual correlation between the tagger and the kinematics of the jet, despite the fact that we made every effort in the training to remove such correlations. One issue, though, is that this single transfer factor actually has to do two jobs. It has to capture the residual correlation and also capture any data to simulation discrepancies in the tagger performance. So if we factorize it, we can actually constrain the residual correlation effects by doing a separate fit to the simulation and then only let the floating parameters in this polynomial transfer factor capture the data to simulation discrepancy. And of course, now you have some transfer factor of arbitrary order. You need some stopping criterion to know when the fit is of sufficient quality so that you don't just overfit or underfit your data. And that's just done by a F-test procedure. So with that, actually, we can jump straight to the results because many of the other backgrounds are quite subdominant, as you see. Essentially, what's left is the resonance peaks of the W and Z and Higgs. At the end of the day, we observe a signal strength of 3.7, which corresponds to a significance over the no Higgs background of 2.5 sigma. And so you see on the left plot, basically a combination over several transverse momentum categories. We have 6 categories that are grouped into one plot in this figure. And on the right, you see an alternative fit where we allow the Higgs signal strength to vary per PT category. Basically, the purpose of this is to assess the compatibility of the different PT categories in the analysis. Of course, all these signal strengths are with respect to some prediction, and that prediction is the LHC Higgs cross-section working group result that I mentioned previously. And so you can see an interesting trend with respect to the transverse momentum. As you go higher, the best fit signal strength increases. Okay, since this previous result had gathered some interest and we wanted to present this in a way that could be more easily reinterpreted, we attempted to unfold a 6 reconstruction level PT-VINs into 3 particle level PT-VINs using the simplified template cross-section binning, which you'll hear a bit more about tomorrow. And then we fixed the other production modes to the standard model expectation. So that is a choice, right? You have a choice of either, you have to choose one particular production mode to unfold. We don't have any discriminatory power amongst the different production modes. So we either choose to fix that production, the other ones to their expectations, or we choose to fix their ratio to the expectations. That was the 2 options. We went with this one. The result of this is basically that the trend in PT that we saw in the alternative fit on the previous slide leads to an excess in the unfolded highest PT bin with a local significance of 2.6 sigma. So the column to look at is the rightmost column on this table, where you have a measured cross-section of about 30 femtobarn versus a predicted one of about 2. So hopefully you get a flavor of what CMS is doing with respect to hadronic Higgs decays. You can see that our most recent successes, both in this result that I just mentioned and also these less recent ones, is mainly due to advancements in deep neural networks for bottom and charm quark tagging and new or improved background estimation techniques to deal with these complicated taggers. And I think the main takeaway here is that a new kinematic regime in Higgs production is now being explored, and that's made possible by the large hadronic branching fractions. And I do hope that other boosted hadronic modes may help probe this high transverse momentum Higgs production as well. So thanks for your interest.
Okay, thank you. Questions or comments on this talk? Valerio.
Hi. So thanks a lot for the very nice talk. I was wondering if you could clarify a bit how you handle the Z peak in the various measurements. Like, do you let it float simultaneously? Does your signal strength on the Higgs depends so much on the Z and something like that?
Right. So in the previous result, there was actually an attempt to measure both simultaneously. In this one, what we saw is you basically have 2 choices in this analysis. You can either choose to trust your auxiliary measurement of the Tagger efficiency, the HPB Tagger efficiency, and probe the Z signal strength, or you can choose to trust the predictions of the Z signal strength and instead probe your Tagger efficiency. In this analysis, we went for the latter, where we actually use the Z as a candle to help constrain the Tagger efficiency so we better know the expected HPB strength.
Okay,
so essentially, yeah, this means the Z is taken from prediction with the corresponding uncertainties.
Maybe one quick follow-up, if I'm allowed. Do we have a feeling of the size of the uncertainty on the Z predictions? Because I had a feeling from your note that your anti-tag region, well, it's still very difficult to take the Z out of there, right?
Right, yeah. I mean, certainly the anti-tag region doesn't tell you the Z normalization that well. But the prediction is basically following the sort of the state-of-the-art scheme that we've seen applied to monojet in similar results, where you want to know to high accuracy the ZPT spectrum. And the associated uncertainties with those are in the sort of 10% regime, if I recall correctly. Theory on uncertainties.
Okay, thank you. I don't see any other questions, so thanks again for the nice talk, Nick. And let's move to our last speaker of the session, Marco.
Sorry, I have to find the stop button. There
So let me share the slide.
Marco, can you share your, oh, okay, very good.
Can you see them?
Yep, we can see the slides.
Last but not least, the measurement and search for the Higgs boson decays to quark pairs with the Atlas experiment, the LAC. So when we are talking about Higgs into quark pairs, essentially we're talking mostly about Higgs into BB bar. Just by the fact that the branching ratio into BB bar is so large, almost 60%, makes this decay to control the Higgs total width, and therefore the branching ratio of the other decays, and by itself this makes this decay especially important. In addition, we know that the Higgs into BB is sensitive to new physics. An example is the shifting between the relation between the coupling and the B quark mass through delta B effect in supersymmetry. We have efficient flavor tagging. The previous talk was an example. So Higgs into BB can also be the main Higgs hadronic decay channel that is accessible as LAC, allowing the best statistics in Higgs processes that either have a small cross-section or they are probing specific corners of the phase space. For Higgs into charm-charm, we are not there yet, partly because of the branching ratio, partly because of the limitation in the flavor tagging capabilities. We had a pioneering analysis in Atlas on part of the statistic that gave a constraint through ZH associated production of the order of a factor of 10 on the coupling enhancement. But now with the run two statistics, not only the static properties, so the couplings are accessible, but also the dynamical properties, differential cross-section, especially the PT distribution, and you have seen the case of CMS in the previous talk. So they are all accessible through BB final states. The Higgs boson production at transverse momentum is interesting because it provides some enhanced sensitivity to the new physics models. They may be even more sensitive through the static properties. And so this is typically analyzed through effects that are encoded in effective field theories. In the case of the gluon-gluon fusion, we are sensitive to the loop nature of the effective GGH coupling. In the case of associated VH or VBF production, we can pin down the tensor structure of the couplings of the Higgs with electroweak gauge bosons. Jet flavor tagging is achieved in Atlas by combining the response of track and vertex-based physics taggers into high-level discriminant, either through based decision trees or deep learning. Working points are selected depending on the needs of the analysis. Both efficiency and the misidentification rates of the non-BB bar or the non-CC bar are measured directly on the data. It is important to see that wherever you are setting your performance, for example, in the lower right plot, if you fix your efficiency, the rejection on non-BB will have always significant PT dependency. It is important as we are going to probe the extremes of the phase space. Higgs into BB gives you access to essentially all the main production channels through a number of signal signatures. I'm not touching here upon TTH, that will be discussed by talk by the colleague Jelena Jovicevic tomorrow. In all the other cases, we can say that there is always, or in most cases, a boson that is radiated, or either a gluon or a electroweak boson or a photon, and this enhances the signal to background ratio. This is very important in gluon-gluon fusion. The VH production remains the main, the queen of the processes due to the triggering capabilities for the electronic decays of the ZNWs and the reduction of the QCD background. Vector boson fusion also may get improved triggering and background rejection in the analysis in association with the high energy photons, and I'm going to show you some examples. The signal to background ratio increases in essentially all of these channels with the Higgs boson PT. So it is interesting to go and analyze towards high PT. However, as the opening angle, we have to remember that opening angle between the two decay products, the two B's, will scale as the mass of the X of the mass of the PT of the X. So this makes the analysis to make a transition between a fully resolved regime to a boosted topology in the PT range of the X between 450 and 650 GeV. In the lower end of this PT range, the Higgs boson are fully reconstructed as a pair of calorimetric jets that are B-tagged. At IPT are reconstructed as a single larger jet with a variable radius jet substructures that can be B-tagged. The reconstruction of the mass of the system, depending respectively if it is resolved or if it is boosted, is of utmost importance for the sensitivity of the analysis because they find the region in which you are integrating your underlying background. Larger jets mass combines their information between tracking and calorimetry. We have mass calibration that is provided over a large PT range by combination of W, Z's, and top, as you can see in the top right plot. And you can also consider improved resolution that is afforded by applying analysis-specific corrections. I mean, these include the contribution of the muon from semi-leptonic decays, so-called muon in jet correction, the correction by the ratio of particle level to reconstructed jet energy, which we call PT RICO, or in the cases in which the X records against an object that can be measured with better accuracy than the X system itself, then a full kinematic fit where the BB system is balanced in the transverse plane with a recoiling system. The improvement these correction are providing go in the range between 5 and 40%, and allows also the migration event from the low tail to the bulk of the peak. And the effect, as you see from the two plots on the bottom, is equally present in resolved jets and in larger jets. So the first analysis that I would like to discuss in detail is a one of associated W and Z production. This is an update of the analysis that gave the first evidence for the X into BB. There are a number of improvements that were made into the analysis, both for the splitting in the PT, the improved BDT and the control and signal region separation, the data-driven estimate of the TT bar and single top background contributions, and the use of the BDT. In the end, you have an analysis that has 3 different lepton channels that categorize events where we have the Z that goes into neutrinos, the double production of the Z that goes into pairs of charged leptons. You have 2 jet categories, and then you have 2 or 3 beams of PT, so it gives you 14 analysis regions in total. And when you include also the signal region and the control region that are defined using the delta R between the two B products, you have 42 regions that are simultaneously given to a beam profile likelihood, while you normalize the V plus jet, the X strengths, and the TT bar backgrounds separately and leaving them unconstrained. The result of the fit is a 6.7 sigma significance for the signal. That is exactly what was expected. Also, ZH and WH production can be obtained separately with the 5.3 and the 4 sigma. The main systematic uncertainty are due essentially to signal modeling, the flavor tagging response, the jet energy scale and resolution, and the modeling of your V plus jet background. A cross-check using a fit on the mass spectrum provides a nice hypothesis shown here and is compatible with the main fit on the BDT response at essentially 1 sigma level. You can do the analysis in differential, in different beams of PT. So 2 beams are made for the W, 3 for the Z. There is a very good correlation between the reconstruct and the true. PTs is ensured that there is very small correlation between the neighboring STXS beams. You can use these results to set limits on effective Lagrangian parameters that are sensitive to anomalous couplings. Here you have sensitivity to Z coupling of the X to the BV, to the QQZV, and to the X into BB bar. For the dimension 6 operators, all the results, as you see, are consistent with the standard model. And you can also go beyond using Wilson coefficients and using constraints on eigendirections that are linear combination of the Wilson coefficient that boost the experimental sensitivity, but also this gives results where the standard model is still at the center of the range highlighted by these results. VBF production looks at events that are characterized by 2 central B jets from the Higgs and 2 light quark jets with larger rapidity gap. The kinematic property used as inputs to a VDT. The signal is unextracted from a simultaneous fit. The first analysis that is already been published is shown here, where the whole hadronic and the photon channel were combined. But more interestingly, means there is a new analysis obtained on the VBF plus gamma production. This is a new search for the full run-2 data set with an event level VDT that classifies events as signal background-like based on a set of kinematic variables. These are chosen to optimize the separation and also to have a low correlation between the mass to prevent a distortion of the MBB spectrum. The VDT output defines regions that are increasingly rich in signal between low VDT, medium, and high VDT. You expect events like the one that is shown here with the forward VBF jets, Higgs candidate B-tagged, and the high energetic photons in the system. The rate of the Higgs is extracted by the simultaneous fit to the B-tag jet pair invariant mass in the 3 event categories. The results are given below the plot that shows the Z and Higgs region on the right. The analysis is statistically limited. The dominant systematic contribution experimental are due to the jet energy scale and the flavor tagging uncertainties. So as observed, the Higgs signal significance is 1.3 sigma. As you can see, this is well in agreement with what we would be expecting. The boosted Higgs production instead looks to events where you have a Higgs boson candidate that is reconstructing as a leading larger jet in the event. Contains at least 2 variable jets associated. The 2 leading of the 2 are B-tagged. PT larger than 250 to have containment inside the delta R equal 1. There has been an analysis on gluon-gluon fusion boosted with the cut at 450 GeV for the leading jet, where the QCD contribution was modeled with a 4th-order polynomial exponential function, and it was tested on an anti-B-tag validation region, while the TT-bar contribution was constrained on the TT-bar control region. The results is given here with 5 sigma for Z plus W and 1.4 sigma for the Higgs, giving a central value of 5.8 with 3 of statistical uncertainty. The more recently, Atlas has presented results on boosted VH, where the reconstruction is similar to the standard VH analysis that I've just presented. In the 0 and 1 lepton channels, the main background is top. In the 2 lepton channels, Z plus jets. The sum of the different contributions to the invariant mass of the fat jet is shown in the plot, like together with a candidate event, with a nice muon from the W and a distinctive larger jet with a substructure of 2 variable jets inside. The results are obtained from a being the maximum likelihood fit of the data to the invariant mass of the fat jet. There are 10 signal and 4 top control regions. The VZ into BB bar and VH into BB bar strengths are extracted simultaneously. The main source of systematic is also here as a larger jet calibration, particularly as a mass resolution and the background modeling. So we have a 2.5 sigma observed VH-PB significance, a 5.7 sigma VZ significance in the PT beams are given in the plot, in the 2 plots on the top for the Z and on the bottom for the Higgs, shown on the right. The mass distribution with the main Z component and the Higgs component are shown on the bottom on the left. Also, this analysis interpreted in the STXS framework in PT beams one being between 250 and 400 GV and one beyond 400 GV. This is justified by the increase in the signal over background, as I've already mentioned, with APT. The sensitivity gain in the determination of the Wilson coefficient is highlighted by having this availability of splitting in beams of PT by the plot shown on the right bottom that shows the result that you obtain by having a single beam or a split beam in PT and using linear and quadratic contributions where you start seeing the way that these measurements are constraining Wilson coefficient of additional contribution to the Lagrangian to which these production decay processes may be sensitive. Time to take conclusion and some perspective. So the studies of the Higgs into BB decays have been performed essentially in all main production modes. The measurement of the combination of production modes is important for the interpretation and as well as the sensitivity to new phenomena. Most of the results that were reported here are already performed on the full run to statistics, with more analyses that are in progress and expected to be completed by the end of the year. There are the first PT differential cross-section results extracted from the boosted VH that can be used using boosted and the resolved VH analysis to constrain Wilson coefficient in effective field theories. It's also interesting that the PT spectrum together with the Higgs into BB coupling can be used to put indirect constraint on the Higgs into CC coupling that are also now the order of what you can do with a direct measurement in ZH into CC. All these results are compatible with standard model expectations with constraints the coupling modifier around 1 of the order of better than 15%. But we have to keep in mind the new physics effect may still be much smaller than the current accuracy, for example, so that are predicted by supersymmetry. This is the reason that we have to do always better. The Higgs into BB remains, therefore, a very active and a constantly improving area. And as the size of statistical and systematic uncertainty in the measurements of the largest sensitivity channels are already comparable, efforts to reduce the systematics further are definitely important for the continuation of this analysis in run 3 and the high gloomy analysis. Thanks a lot.
Okay, thank you, Marco. Questions or comments on this nice talk?
Yeah,
okay,
maybe I can.
Go ahead.
Hello, Tomasz speaking. So I just wonder, I noticed that in the VBF pulse gamma analysis, slightly over integrated luminosity is used. So can you remind us what was the reason for that? Yes, this 132 from inverse to bounds.
From under 39, I think these are just quality cuts due to the presence of the photon. I think it should be something.
Okay.
Here's just I can complete it. Indeed, and the BJet trigger that was used in the analysis was not available in the full data.
Any other questions, comments for Marco? Maybe, yeah, I have a curiosity actually on slide 7. So you showed this table for the bounds on these higher order operators. I see that some of them, as the last one that you show here, has this double solution. I wonder how it is, if it would be possible to exclude the second solution somehow.
Okay, so this is the corresponding.
Very good. Yeah.
Lot. Sure. Well, you already have seen in the case of the boosted analysis that if you have enough information on the PT, then you can start squeezing in. So this is the case, for example. This is a kind of when you consider linear and quadratic terms. So basically, you don't have you only have the dimension 6 operator. You don't have the dimension 8 operators. The contribution of new physics and the standard model, dimension 6 and dimension 8, they come a different order with linear and quadratic dependencies on your coefficients. But already you can see here that if you have enough information on the transverse momentum, you can definitely start excluding some of these double solutions. I mean, so eventually when more of this data will be available, yes, certainly this will be possible.
Yeah. Okay, very good. Thanks. Yeah, I don't see any other question. So thanks again, Marco, for the nice talk. And I wanted to mention that indeed the Zoom room will be still open for an hour for discussions and additional questions for the speakers if there are any. And otherwise, yeah, we'll resume again tomorrow. Thanks to all the speakers of this session.
Thanks to you.